Hello my dear students, welcome to IMS GATE Academy. Very good evening one and all. I hope all of you are attending our quick revision sessions. So whether any new students are there who are attending very first time in our YouTube channel. Yeah, I hope all of you are attending our quick revision sessions, right? So in this particular session, we are going to discuss regarding digital circuit subject. This subject is one of the most important and scoring subject for 4 branches according to GATE exam point of view: EC, electrical, instrumentation and computer science. So all of you kindly share this video link with all of your friends so that they also will attend this session in live and they also will get benefited from this session, right? So in this particular session, from each and every chapter, all the important topics, okay, from all the topics I will discuss all the important points and formulas so that all of you will get regarding this entire subject, regarding digital circuit subject, you will get complete picture, okay, you will get the confidence about this particular subject. Yeah, good evening everyone. Good evening Saurav, good evening Sasmal. Yeah, eagerly waiting for the session. Yeah, thank you. So I hope all of you know the syllabus of digital circuit subject. So here we are having total 7 chapters. Yeah, good evening Jagdish, good evening Amol. Yeah, very good evening one and all. So here first chapter is number systems and codes. Second chapter is Boolean algebra and K-maps. Third chapter logic gates implementation. And fourth chapter combination circuits. Fifth chapter sequential circuits. And sixth chapter data converters, and the last chapter, 7th chapter, CMOS logic family. CMOS logic family. So here first 5 chapters for CS branch, the syllabus is up to 5th chapter, whereas for electrical branch up to 6th chapter. For EC and IN, all the 7 chapters. For EC and IN, all the 7 chapters is part of the GATE syllabus regarding digital circuit subject. So coming to the weightage point of view, for CS branch and electrical branch, the weightage will be 4 to 5 marks, whereas for EC around 8 marks. For instrumentation, it will be from 8 to 10 marks. So this is one of the most important and scoring subject and which is common for 4 branches: EC, electrical, instrumentation and computer science, right? So that means if you observe with respect to syllabus, branch wise also if you observe, among all the 7 chapters, the first 5 chapters are very, very important for all the 4 branches, right? So first let us start with number systems and codes. So all of you put the heading, chapter 1, number systems and codes. So first let us discuss regarding number systems and then related to binary codes. So in our day-to-day life also we are using one number system. What is that name of the number system? In our daily life we are using one number system. What is that? Yeah, good evening Nikhil. Very good evening one and all. In our day-to-day life, in our daily life, we are using decimal number system. Yes, very good Amlan, very good. So in our daily life, we are using one number system that is called decimal. So in the decimal number system, if you are having the single digit, yes, very good Amol, very good. If you are having a single digit, we can represent 10 possible values, 0 to 9. Any value we can represent for a single digit. Since there are 10 possible values we can represent for a single digit, base of the number system is 10. Base of the number system is 10. Okay. Now, if you are considering base of the number system is R, then in any number system for a single digit, you can represent the starting value from 0 and maximum value you can represent R minus 1. If the base of the number system is R, the max value that you can represent for a single digit is r minus 1. Okay, so if you consider base value as 2, you can represent either 0 or 1, two possible values. That means the number system name is binary number system. Okay, similarly, if you consider base is 3, r is 3, then you can represent 0, 1, 2. Three possible values you can represent for a single digit. So base value is 3, base 3 number system. Similarly, if you consider base is 4, then you can represent 0, 1, 2, 3. Four possible values are there. So the corresponding base is base 4 number system. In this way, you can have various number systems. For the time being, I am choosing r is 8. If you are choosing r is 8, you can represent 0 to 7. What is the name of the number system? I hope all of you are familiar. If base is 8, what is the name of the number system? Yes, it is octal. Very good, Amol, Amlan. Yes, it is the octal number system. Similarly, if I am considering base is 16, according to the formula, since r is 16, it is starting from 0 and maximum value should be 16 minus 1, that is nothing but 15. But if you are using single digit, the maximum value that you can represent 9 only. So that means here we will represent 0 to 9. 10 to 15 we cannot represent with the help of single digit, so we will use alphabets. For representing 10 to 15, we will use alphabets. So that means 10 is nothing but A, 11 is nothing but B, like that 15 is nothing but F. So here you are having total 16 possible values. So the name of the number system is hexadecimal. Hexa means 6, decimal means 10. So together it is the hexadecimal. Okay, right. Say for example, if I give one number 1, 2, 3, 4. You are having a 4-digit number 1, 2, 3, 4. Okay, just by looking at this number, can you say that this number exactly belongs to so and so number system? Is it possible? If you are having a 4-digit number 1, 2, 3, 4, okay, can you say this number exactly belongs to so and so number system? It's not possible, right? But you can guess. See, this particular number is valid in which number systems? I hope all of you can answer. This number is valid in which number systems? Yes, very good, Amol. Others also please respond. Yeah, we are getting different answers. Yes, very good, Amlan. Yeah. Now if you observe here, you are having a 4-digit number 1, 2, 3, 4. Okay, just focus about the individual digits. Among all the digits, 4 is the maximum. Right? So that means this particular number is valid in base 5, base 6 and so on, and in all other higher order number systems, right? So that means here one important relation is there. This is very, very important. So the base of the number system R should be greater than or equal to maximum value of a single digit plus 1. So this is very, very important formula. Base value is always greater than or equal to maximum value of a single digit plus 1. So here among individual digits, single digits, among all 4 is the maximum. So just apply this relation. R is greater than or equal to 4 plus 1. So that means R is greater than or equal to 5. So it is valid from base 5 and even in other higher order bases it is valid. Okay. Suppose, see, in the GATE exam you will get some equations. Okay. They will give few numbers and they won't mention the base value. They will represent base as X or R. Okay. You have to find out what is the base value. That time what you have to do, after solving a particular equation, you may get few roots. Okay, whatever the roots you are getting, those are theoretical, but all those roots may be valid bases or may not be valid bases. In order to say whether whatever the solutions you are getting regarding the base, whether those are valid or not, you have to apply this particular relation. Whichever roots are satisfying this particular relation, all those are valid bases. Say for example, you have solved one particular equation. After that, regarding the base, suppose if you got two roots, like one root is 3, another root is 5, suppose you got, okay. So see, just if you apply this particular relation, then with the help of this one, only 5 is satisfying but 3 is not satisfying. So you can eliminate like that. Or even you can represent this number. Suppose you got one of the root as 3, okay, regarding base. You mention here 3. If you are having 3 here, is it possible to represent the digit as 3 in base 3 number system? Is it possible to represent digit as 4 in base 3 number system? Suppose after solving a particular equation regarding base, you got R value as 3. Okay, if you are considering 3 here, then in the base 3 number system, is it possible to represent 3 and 4? No, not possible, right? So theoretically, you may get n number of solutions, but all those solutions may be valid or may not be valid. Whichever solutions are satisfying this relation, all those are valid. So in that way, you can cross-check whenever you are solving any question related to the base, whether those theoretical solutions, whether all those solutions are correct or not. You can just consider that particular base. After that, you can analyze, or with the help of this formula also you can analyze, right? I hope it is clear for everyone. This is one of the most important formula whenever you are calculating regarding base, okay. See, regarding this relation, nowhere in the question they will mention in the question, nowhere they will mention regarding this particular relation, but you have to apply this particular relation. This relation is inherently present. If you are able to apply this relation, whatever the roots are satisfying this relation, all those are valid bases. All those are valid bases. I hope it is clear regarding the base and whatever the prominent number systems we are having: decimal, binary, octal, hexadecimal. Okay, now let us see the number system conversions. So for the time being, I am considering decimal number. Let us convert decimal number into any other number system. For generalized case, I am discussing decimal number to any other number system. So that means you are having one decimal number. Now we want to convert into some other number system which is having base R. Base R. Say for example, if you are having the decimal number 135, so all of you just do this conversion. 135 is the decimal number. Convert this number into base 4. All of you give a try. This is a simple question. You are having the decimal number. Convert this number into base 4. See, whenever you are having any integer, okay, if you are performing division with 4, whenever you are having any integer number, okay, if you are performing division with 4, what are the possible remainders you will get in general? Whenever you are dividing any integer with 4, what are the possible remainders you will expect? You will get in general. Yes, you will get 0, 1, 2, 3. Yes, very good, Amlan. Very good. Okay. So that means 0 to 3 belongs to 0, 1, 2, 3. These digits belongs to base 4 number system. Base 4 number system. Right. So that means here in this case we will perform repetitive division with the 4. Yes, very good, Anand. Very good. So here we will perform repetitive division with 4. So here the given number is 135. Perform repetitive division with 4. 4 3s are 12. Remainder is 1. And then you are having 5. So once again 4 3s are 12. Remainder is 3. Next 4 8s are 32. Remainder is 1. 4 2s are 8. Remainder is 0. 4 zeros are 0. Remainder is 2. Okay. So in this way, just perform the division operation, place the quotient here and place the remainder here. Okay. Like that, continue the process till you are getting quotient as 0. Once if you are getting quotient as 0, you can stop the process. Right. Now, whatever the remainders you are getting, you have to consider the reverse order while you are placing the digits from left to right. So this is the remainder you got lost. That will be your starting digit 2, then 0, then 1. And whatever the remainder you got first, that will be your last digit 2013. Yes, very good, Anand. 2013. So 2013 is the base 4 number system, base 4 number which is equivalent to the given number 135. Next, consider fractional number 0.125 base 10. Let us convert into base 4. See, previously we have considered integer part. For integer part, you have to perform repetitive division with the corresponding base. Okay. Now let us consider fractional part. So here exactly opposite process we will do. Exactly opposite. Here repetitive division we have performed. Now here we will perform repetitive multiplication with the corresponding base. So 0.125 into 4. Now, see, I hope all of you know this one. 1 by 2 is nothing but 0.5. Just divide this number with 2. You will get 1 by 4, which is nothing but 0.25. Once again divide with 2. You will get 1 by 8, which is nothing but 0.125. So here you are having 0.125, which is nothing but 1 by 8. So 1 by 8 when you are multiplying with 4. 1 by 8 when you are multiplying with 4, you will get 1 by 2. 1 by 2 is nothing but 0.5. So after doing multiplication, whatever the integer you are getting to the left of the radix point, you have to consider that integer. In this case, you are getting 0. Just take that 0. After taking 0, here equivalent value will remain same. So continue further. Multiply with 4. So 0.5 into 4 is nothing but 2.0. So in this case, you are getting an integer 2. You can consider that integer 2. After taking the integer 2, here the digits are becoming 0. All the digits become 0. You can stop the process. Here the moment you are getting quotient as 0, you can stop the process. Similarly here, after performing few iterations, whenever you are getting all the digits are 0s, you can stop the process, or based on the given choices, after the radix point, how many digits you are having, accordingly you can perform number of iterations, right? So here in this case, whatever the integers you are getting, we will place in the normal order after the radix point. After the radix point, we will place in the same order, 0, 2. So here 0.02 base 4, which is nothing but 0.125. Yes, very good, Anand, very good. So in this way, whenever you are having integer part, you can perform repetitive division. Whenever you are having fractional part, you can perform repetitive multiplication. The same procedure you can perform for any number system. If they ask binary, you will consider here in the place of R 2. Okay. If they ask octal number, consider 8, like that. If they ask hexadecimal, you can consider R as 16. Like that, you can continue. Okay. So in this way, you can convert decimal number into any other number system. This is the integer part. This is the fractional part. If you combine both, it is the real number. Okay. So 135.125, if you are having, so first you can perform for 135, then you can perform for 0.125. After that, you can combine. That's all. Okay, right. I hope it is clear for everyone how to convert decimal into any other number system. Now let us see any other number system into decimal. Any other number system into decimal. Next one, any other number system into decimal. So that means here we are doing the conversion of a number from radix r into the decimal equivalent. Right. So for easy understanding, let us consider what are the numbers just now we got. 2013 we got base 4. 2013 base 4. So let us convert this one into the corresponding decimal equivalent. See, here you are having 4 digits and here these digits belongs to base 4 number system, right? So whenever you are supposed to find the equivalent value or whenever you are supposed to find the decimal value, both are same. So each and every digit is having respective positional weight in powers of the corresponding base. Here base is 4, that means the positional weights are 4 power 0, 4 power 1, 4 square, 4 cube, right? Each and every digit you have to multiply with the respective positional weight and then you can add. Okay, so 4 cube is nothing but 64 into 2. 64 into 2 plus 4 square is 16. 16 into 0 is nothing but 0 plus 4 into 1 is nothing but 4 plus 4 power 0 is 1. 1 into 3 is nothing but 3. 64 into 2, that is nothing but 128 plus 4 plus 3 is nothing but 7. So you are getting 128 plus 7 is nothing but 135. 135. So this is the decimal number. So if you observe, previously I have considered 135, that is the decimal number. The equivalent base 4 number I got 2013. Now I have considered the same number 2013, and while I have converted into decimal, I am getting the same number 135. Right. Similarly, let us perform for fractional part 0.02 base 4. 0.02 base 4. 0.02 base 4. Let us convert this one into decimal. Now tell me what is the positional weights here. For 0, what is the positional weight? For 2, what is the positional weight? Yeah, thank you, Vipin. Yes, in this case, you will get negatively increasing powers of the base. See, when you are having only integer part, positively increasing powers of the base. Positively increasing powers of the base, right? For fractional part, negatively increasing powers of the base. That means 4 power minus 1, 4 power minus 2, right? So here also follow the same procedure. 4 power minus 1 into 0 is nothing but 0 plus 2 into 4 power minus 2 we can write as 1 by 4 square. 1 by 4 square. Okay. So 2 into 1 by 4 square is nothing but 16. So 2 8s are 16. So 1 by 8. Just now we have told 1 by 8 is nothing but 0.125. 0.125. 0.125. Okay. So we got the same number, right? Earlier I have considered 0.125. It is a decimal number. The equivalent base 4 number we got 0.02. Okay. So the same number I have considered, I have got the 0.125. Okay. Base 4 number we have converted back into the corresponding decimal equivalent. Okay. In this way, whenever you are having any other number system, okay, if you are having real number directly, that means integer part and fractional part combinedly, directly you can calculate the equivalent value. Okay. So in this way, you can convert any other number system into base 10. Suppose if you are having octal number, here positional weights in powers of 8, here negatively increasing powers of 8. Similarly, if you are having 16, R is 16, then here positional weights in powers of 16 you will get positively, and here negatively increasing powers of 16, like that. In this way, you can convert any other number into the corresponding decimal equivalent. I hope it is clear for everyone. With the help of these two conversions, we have covered most of the conversions. Decimal number into any other number system into decimal. Okay. See, you might be having the doubt that why I have performed repetitive division here, why I have performed repetitive multiplication here, why not volta? Why not volta? See, Just observe here and tell me, when you're having the base 4 number system, in order to find the equivalent decimal value, here what kind of operation you are performing? Can you tell? Towards left hand side, what kind of operation you are performing with respect to positional weights? All of you please respond. Whether you are performing repetitive multiplication or whether you are performing repetitive division. Which operation you are performing? Just observe from right hand side towards left hand side with respect to positional weights. Is it repetitive multiplication with the corresponding base, or is it repetitive division with the corresponding base? Repetitive multiplication. Yes, very good, Amlan, very good. It is the repetitive multiplication operation we are performing. So that's why if you observe here, for integer part, I have performed exactly opposite process, that is called repetitive division. Okay. Similarly, if you observe here fractional part, here if you observe the positional weights, towards right hand side, here 4 power minus 1, if you are dividing with 4, you will get 4 power minus 2. So that means towards right hand side, repetitive division operation is taking place for fractional part, right? So that means we have to perform exactly opposite process, that is called repetitive multiplication. I hope it is clear for everyone. Why I have done repetitive division here, why I have done repetitive multiplication here, why not will talk. Okay, I hope it is clear for everyone. Now let us proceed to the next conversion, that is, if you are having base R number system, okay, base R number system into base R power n number system, base R into base R power n. Okay, suppose if you want to convert binary number into octal number. Suppose if I want to convert binary number into octal. Okay, in binary number system base is 2, in octal number system base is 8. 8 we can write it as, in terms of 2, you can write it as 2 power 3. So that means if you consider 3 bits of the binary number, just do the grouping of 3 bits, you will get the corresponding octal digit. Similarly, if you are having octal digit, if you want to convert into binary, just represent each and every octal digit with the 3 bits like that. Yes, very good, Amol, very good. Okay, very good. Next one, if you are having binary number, if you want to convert into hexadecimal, binary number into hexadecimal. Okay, so in the binary number system base is 2, in hexadecimal number system base is 16. 16 we can write as 2 power 4. So that means if you consider 4 bits of the binary number and then do the grouping, then you will get the corresponding hexadecimal digit. Similarly, if you are having hexadecimal digit, if you convert into 4 bits, you will get the corresponding binary number, vice versa. Yeah, thank you, Aditya. Okay, so in this way you can convert binary into octal, octal into binary, binary into hexa, hexa to binary, right? Similarly, if you are having binary number, if you want to convert into base 4, now can you tell how many bits we have to do the grouping so that you will get base 4 digits? How many bits, if you do the grouping here, you will get the corresponding base 4 digits? Yes, very good, Purnima, very good Amlan. Yes, very good. See, you follow the same approach, corresponding base 4 digits you will get. Okay, right. Similarly, vice versa. If you are having base 4 digits, if you want to convert into binary, each and every digit you can represent with 2 bits. Right? Similarly, if you are having base 4, if you want to convert into base 16, base 4 into base 16, here also the same logic will applicable. So here base is 16, 16 we can write as 4 square. That means if you consider 2 digits of base 4, just by doing the grouping of those 2 digits, you will get the corresponding hexadecimal digit. Right. So the same logic will applicable if you are having base 3. If you want to convert into base 9. Here base is 3, but here base is 9. 9 we can write as 3 square. So that means here if you are doing the grouping of 2 digits of base 3 number system, then you will get the corresponding base 9 digit. Wherever you are getting powers like this, okay, in this way you can convert base r into base r power n or base r power n into base r. I hope all of you got the clarity. Whenever you are having the conversion from one number system to another number system, regarding those bases, whenever you are having the power of that particular number, then you can do the conversion like this, right? Yes, Samlan. Okay. Say for example, I will consider simple example. Say for example, if you are having 1 0 1 0 0, 1 0 1 0 0. So this is the binary number. If you want to convert this one into base 4, okay. If you want to convert this one into base 4, you can do the grouping of 2 bits. So here 0 0 is nothing but 0. Next 1 0 is nothing but 2. 1 0 is nothing but 2. Okay. Now I am considering the same number 1 0 1 0 0. Now if you want to convert this one into octal, we will do the grouping of 3 bits. 101 is nothing but 5 and 000 is nothing but 0. Okay, 000 is nothing but 0. Right. In the same way, I am considering the same number 1 0 1 0 0. Now if I want to convert into hexadecimal, in this case we will do the grouping of 4 bits. 1 0 0 is nothing but 8. Next, here we have to do the grouping of 4 bits, but we are having only 2 bits. The other 2 bits we can put simply zeros. 0 0 1 0 is nothing but 2. 0 0 1 0 is nothing but 2. So 28 base 16. Right. Similarly, now if you observe, this is the base 4 number. If you want to convert base 4 into base 16, we have to do the grouping of 2 digits because 16 is nothing but 4 square, right? So just do the grouping of 2 digits. Here also I have to do the grouping of 2 digits, but I am having only 1 digit. Other digit you can put simply 0. Now here you are having 2 0, right? See, 2 0 base 4. Another one is 0 2 base 4. Okay. See, when you are having 2 digits, the corresponding positional weights, you will get 4 power 0, 4 power 1. So 4 into 2, 8 plus 0 is nothing but 8. Similarly here, 4 power 0, 4 power 1. So 4 into 0 is 0 plus 2. Okay. So that means regarding 2 0, you are getting the corresponding digit is 8. And regarding 0 2, you are getting 2. Belongs to base 16. Whether both are same or not. Is it clear, Amlan? If you are having base 4 number, if you want to convert into base 16, you have to do the grouping of 2 digits. Just like base 2 into base 4, we have done grouping of 2 bits. Okay, in the same way you can proceed. Similarly for base 3 to base 9. Okay, right. In this way it will applicable. Only thing, whenever you are doing the grouping of 2 digits, the respective positional weights you will get in powers of the corresponding base, like that. Okay. Okay, so similarly, if you want to convert, say for example, octal into hexadecimal. If you want to convert octal into hexadecimal, what you can do, first you can convert octal into binary, and then whatever the binary number you are getting, you can convert into hexadecimal. Similarly, reverse, hexadecimal to octal if you want, first you can convert into binary, from binary you will get octal, right? So in this way you can do any conversion, whatever the number system they can give. If they ask to any other number system, you can do the conversion with the help of whatever the conversion so far we have discussed. With the help of this, you can attempt any question in the GATE exam regarding number system conversion, right? Sometimes they will ask directly the question based on number system conversion. Sometimes they will ask application oriented. That means while solving a particular question, whatever the conversion process we have discussed, that may be useful, right? Now let us see the next topic, that is basic arithmetic operations. So all of you please respond, what are the basic arithmetic operations we are having? Among all the operations, what are the basic? What are the basic arithmetic operations? I hope all of you are very much familiar. Yes, very good Amol, very good. Yeah, the basic arithmetic operations are addition and division. Sorry, addition and subtraction. Addition and subtraction, these two are the basic arithmetic operations. Addition and subtraction. After that you will get multiplication and division. Multiplication is nothing but repetitive addition. Division is nothing but repetitive subtraction, like that. Okay, but the basic arithmetic operations are these two, addition and subtraction. Addition and subtraction. Okay, see, whenever you are performing addition of two single digits of any number system, whenever you are performing addition of two digits of any number system, as long as you are getting the resultant sum is less than or equal to maximum value of that particular digit which belongs to that same number system, so that time you can represent with the help of single digit. Okay, but whenever it exceeds the capacity of that particular single digit, that time we require one more additional digit, right? So this particular digit we will call it as sum digit, and the other digit we will call it as carry digit. Carry digit. Okay, say for example I am considering, for easy understanding, I am considering decimal number system 5 and 9. I am performing addition 5 plus 9. See, if you are having decimal digit, the maximal you can represent 9. But now after performing addition of these two, your resultant sum you cannot represent with the help of single digit, right? So you require one more additional digit. So 5 plus 9 is nothing but you are getting 14. Okay, so here 14 is the decimal number. 14 is the decimal number. So here you are having two digits. The corresponding positional weights are 10 power 0 and 10 power 1. 10 power 0 and 10 power 1, right? So 10 power 1 is into 1 is nothing but 10, plus 10 power 0 is nothing but 1. 1 into 4 is 4. So 10 plus 4 is nothing but 14. See, that is the beauty of the decimal number system. Because the base is 10, after finding the equivalent value also, whatever the digits you are having, the same number you are getting. Okay, whatever the initial number you are having, after finding the equivalent also, you will get the same digits only. That is the beauty of decimal number system. Whereas for other number systems, it will vary. Okay, right. But here if you observe, whenever we are performing addition of two single digits of any number system, whenever it exceeds the maximum capacity of that particular single digit, obviously we require the carry. And always we will represent carry as 1 only. Always we will represent carry as 1, but what is the equivalent value of the carry? Can you tell? Here always will represent carry as 1, but the equivalent value of carry is how much? All of you please respond. Equivalent value of carry is how much? Yes, very good Amol, very good. Yes, it is the base. See here in this case I have assumed that these digits belongs to base 10 number system. Okay, base 10 number system, that's why you got 10. But for generalized case, it will be base of the number system. Yes, very good Purnima, very good. Equivalent value of the carry is nothing but base of the number system. So this is the one of the most important formula. Whenever you are performing addition in any number system, whenever you are unable to represent with the help of single digit, obviously you require one more additional digit. that additional digit is nothing but carry. Always we will represent carry as 1, but the equivalent value of carry is nothing but base of the number system. Base of the number system, right? Similarly, when you are performing subtraction, say for example, I am considering 2 digits. Both the numbers belongs to decimal only. Okay, both the numbers belong to decimal. Okay, for the timing I am considering 35 and 19. 35 is one number, decimal number. 19 is another decimal number. Okay, when you look at these two numbers, obviously 35 is larger when compared to 19. Okay, when compared to 35, 19 is smaller, right? That means you can perform subtraction operation. You can perform subtraction operation. But while you are performing subtraction operation, when you observe these two digits, you have to perform subtraction like 5 minus 9. Is it possible? Whether you can perform direct subtraction 5 minus 9, is it possible? No, not possible. That time we require borrow. Yes, very good Amol. 5 minus 9 you cannot perform, so we require borrow. Okay, so just like here, if you observe, the moment you are getting carry, the equivalent value of carry is nothing but base. Okay, in the same way, yes, very good Sachidanand, yeah, very good. So just like in the same way, now here we require borrow. Whenever we are, see, if you are subtracting smaller digit from larger, you can perform direct subtraction. But whenever you want to subtract the larger digit from smaller, direct subtraction not possible. That time you require borrow. Okay, since you are taking borrow from the next higher digit, the equivalent value of borrow, in this case you will get 10, because I have considered base of the number system is 10. Okay, so now 10 plus 5 is nothing but 15. From 15 minus 9, you will get 6. Okay, see, up to here most of the people will do correct. In the exam also most of the students will perform up to here correct, but most of the students will forget subtracting 1 from where we have taken borrow. See, since we have taken borrow from here, we have to subtract 1 from here. So 3 minus 1 is nothing but 2. 2 minus 1 is nothing but 1. Okay, so that means whenever we want to subtract the larger digit from smaller, that time direct subtraction not possible. We will take the help of borrow. The equivalent value of borrow is nothing but base of the number system, just like here. So you can make a note, equivalent value of borrow is nothing but base of the number system. So if you are performing octal subtraction, that time equivalent value of borrow will be 8. If you are performing hexadecimal subtraction, equivalent value of the borrow is nothing but 16, like that. Okay, right. I hope it is clear for everyone up to this point, whatever we have discussed. Okay, now let us proceed to the next topic, that is data representation. Data representation. Okay, right. See, in general, we can classify the numbers into two types. First one is unsigned numbers. And second one is signed numbers. In general, we can classify the numbers into these two categories. As the name implies, here unsigned, that means here there is no sign in front of the number. That means whenever you are having set of positive numbers, when you are having only positive numbers including 0, set of positive numbers including 0, that time we no need to represent any sign in front of the number, because by default all those numbers are positive only, right? Here no need to represent the sign in front of the number. Okay, so that means here you will be having in the binary number, the representation wise you will be having n number of bits. You will be having n number of bits. Okay, each bit will be having respective positional weights in powers of 2, 2 power 0, 2 power 1, 2 square, and so on. And last digit positional weight will be 2 power n minus 1. 2 power n minus 1. Right. Now, if you observe among these positional weights, this one is the least. So that means this particular bit we will call it as LSB. It is having least positional weight, whereas this leftmost bit having maximum positional weight. So that's why we will call this bit as MSB, most significant bit. Okay. So whatever the number of bits we have considered here, all the bits together giving the magnitude of that particular number. Magnitude of the number. Okay. So this is the representation we will follow for unsigned numbers, right? See, in the question, whenever you are having binary number, if they don't specify that number belongs to which representation it is, by default it is the unsigned. Okay, by default it is the unsigned. All the bits together give the magnitude of that particular number. Okay, whereas regarding signed numbers, so that means here, as the name implies, sign is there. That means whenever you are having set of both positive numbers and negative numbers, that time it's mandatory to represent the sign in front of the number, right? Suppose if you are having plus 5 and minus 5. Okay, so in order to distinguish whether it is positive or negative, here we are representing the sign, plus sign or minus sign. Okay, in the conventional number system, right? So that means here we are using one bit. Okay, so with the help of that bit, we are able to identify whether it is a negative number or positive number. Okay, so regarding signed numbers in binary, we are having three forms. First one is sign magnitude form. And the next one is one's complement form. And third one is two's complement form. So we have three forms for representing signed numbers in binary. Okay, right. So let us see one by one. Here, as the name implies, sign is there, magnitude is there. Okay, right. See, in general, in the conventional number system, whether it is positive or negative, with the help of sign, plus sign or minus sign, with the help of this sign, we are distinguishing whether it is positive or negative. But here in the binary, everything we have to represent in terms of zeros and ones. Okay, but luckily, since you are having only two types of numbers, one is positive, another one is negative. Okay, so here with the help of one bit, we can distinguish whether it is positive or negative. So here the leftmost bit we are reserving for sign bit. This is the sign bit, and the remaining bits give the magnitude. Okay, so if the sign bit is 0, which indicates positive number. If the sign bit 1, it indicates negative number. Say for example, plus 5 if you want to represent in sign magnitude form, plus 5 is nothing but, here plus sign is there, so that means sign bit should be 0. And regarding 5, I hope all of you are familiar, 101. 101 is nothing but 5. Now similarly, if you want to represent minus 5, here minus sign is there, so that means sign bit should be 1. Regarding magnitude bits, same as it is, 101. Right. See, just like in the conventional number system, whenever you want to convert a positive number into negative number, the magnitude remains same, only the sign is getting changed, right? Plus to minus or minus to plus, right? In the same way, in the sign magnitude form, the magnitude bits remain same. Only the sign bit will be complemented whenever we want to convert positive number into negative number or negative number into positive number, right? Okay. And one more important point, whatever the representation we got, 0, 1, 0, 1. 0, 1, 0, 1 is nothing but what? Plus 5. Okay. The same 0, 1, 0, 1 is nothing but plus 5 in 1's complement form, in 2's complement form. This is one of the most important point. The representation of, you can make a note, the representation of positive numbers, is same in all the three forms. the representation of positive numbers is same in all the three forms. Okay, so whatever the positive number representation you are getting in sign magnitude form, the same representation is applicable in 1's complement and 2's complement. Yes, correct, Amol, correct. Yeah, that point I will come to. Yeah, I will discuss after some time. Yeah, that's true. The representation of positive numbers is same in all the three forms. Okay, now regarding negative number representation, based on the notation or convention, you will get different representations. Okay, according to the sign magnitude notation, you are getting 1101. Now let us see in 1's complement what we are going to get. If you want to represent -5 in 1's complement form, you have to apply 1's complement for positive number. If you apply 1's complement to positive number, then you will get -5. Okay, so just now I have mentioned +5 is nothing but 0101. So 1's complement of 0101. Okay, as the name implies, 1's complement means just you have to replace wherever zeros are there, replace with 1, wherever 1s are there, replace with zeros. That's all. Okay, so that means you will get 1010. 1010. So that means 1010 is nothing but -5 in 2's complement form. 1010 is nothing but -5 in 2's complement form. Okay, similarly, if you consider 1010, if you apply 1's complement, all of you please respond what is the number you are going to get. I have considered this number, just apply 1's complement. What is the number you are going to get? Yes, very good, Amlan, Anand. Yes, you will get 0101. 0101. So that means just from here you will come to know. See, here you are having sign bit 1. See, whenever they mention that 1010 is represented in 1's complement form, if you are supposed to find what is the equivalent value, okay, so just by looking at the sign bit, since sign bit is 1, it is a negative number. Sign bit 1 indicates negative number. Okay, but if you want to know what is the magnitude, consider this number, apply 1's complement. From here you are getting the magnitude. 101 is nothing but 5. 101 is nothing but 5. Okay, similarly, if they specify that 0101 is represented in 1's complement form, 0101 is represented in 1's complement form, that time just by looking at sign bit, since sign bit is 0, it is a positive number, and 101 is nothing but 5. So the moment if sign bit is 0, you can follow sign magnitude convention. The moment if sign bit is 1, okay, from there you are getting it is a negative number. But in order to know what is the magnitude, just apply the corresponding complement. Okay, so in this way, if you observe, we have considered positive number. See, whenever in the question representation is there, if you are having positive sign, sign bit should be 0. If you are having negative sign, that means sign bit should be 1. That is the indication whenever representation is there. Okay, and similarly, you have considered positive number, and if you are applying 1's complement, you are getting negative number. Similarly, I have considered negative number. If you are applying 1's complement, you are getting positive number, right? So in this way, you can convert positive number into negative number into positive with the help of 1's complement. Now let us see regarding 2's complement. 2's complement is nothing but 1's complement plus 1. Just by adding 1 to the 1's complement, you will get 2's complement, right? So if you want to represent -5 in 2's complement form, so you have to apply 2's complement for positive number, that is plus 5. So just now I have mentioned 2's complement is nothing but 1's complement plus 1. So 1's complement of plus 5, just now we have calculated, we are getting 1010. So for this number, just you can add 1. Just add 1. So you will get 1011. Now consider this number. All of you just apply 2's complement. What is the number you are going to get? All of you please respond. Just consider this number 1011. Just apply 2's complement. What is the number you are going to get? Yeah, thank you, Ankit. Thanks a lot. All of you try. Just consider this number, apply 2's complement. All of you please respond. What is the number you are going to get? Yes, very good, Anant, Amol. Yes, you are going to get, see, just apply one's complement, you will get 0 1 0 0. After that you can add 1, so that means you are getting 0 1 0 1, right? So here, just by looking at the sign bit, since sign bit is 1, it indicates net number. In order to know what is the magnitude of this particular number, just consider this number, apply 2's complement. From here you are getting magnitude. 101 is nothing but 5. Just like the procedure, whatever I have discussed for 1's complement. Okay. See, the moment if you are having sign bit as 0, you no need of any confusion. The remaining bits simply give the magnitude. That's all. Whether it is sign magnitude or 1's complement or 2's complement, the given number is. Okay. But whenever you are having the given number, okay, if you are having sign magnitude form, if the sign bit is 1, it indicates minus. After that, remaining bits give the magnitude. This is according to sign magnitude. Okay. Now, if you are having negative number like this, okay, and if they mention this number is represented in 1's complement form, just by looking at the sign bit, since it is 1, it is a negative number. In order to know the magnitude, just once again apply 1's complement. From there, you are getting the magnitude. Okay. Same procedure here also. I hope it is clear for everyone. This is one procedure. Whenever they mention any particular number, suppose 1011, if they mention that this number is represented in 2's complement form, what is the equivalent decimal value, right? So just by looking at the sign bit, you are getting it is a negative. The moment if you are getting negative, in order to know the magnitude, apply the corresponding complement method. This is one procedure. Now I will give the easiest procedure. You no need to do this conversion. Okay. Whenever you are having one number, if it is already represented in 2's complement form, in order to get directly this value, I will give the shortcut. So all of you please pay attention. Now, if you are having unsigned number, just you will place the position weights like this in powers of 2. Now, since they have mentioned this number is represented in 2's complement form, just by looking at the sign bit, since you are having sign bit as 1, the corresponding position weight is minus. Sign bit 1 indicates negative number. The respective position weight you have to consider minus. That's all. Okay. Now wherever ones are there, just add respective position weights. Minus 2 cube is nothing but minus 8 plus 0. Then 2 power 1 is nothing but 2 plus 2 power 0 is nothing but 1. 2 plus 1 is nothing but 3. Minus 8 plus 3 is nothing but minus 5. In this way, directly you will get the value. Okay, it is very simple. Now you might be having the doubt, if they mention 0101 is represented in 2's complement form, if I want to know what is the corresponding decimal equivalent, yes, you can do. See, in general, what you will do, you will place the position weights like this. Okay. Since sign bit is 0, it indicates what? Positive number, right? Anyway, by default, we are considering all the position weights are positive. Okay. But only the difference is, since sign bit is 0, I will put whatever the equivalent value you are getting, I will put plus sign in front of the number. That's all. Okay. 101 is nothing but 5. I hope it is clear for everyone. Okay. Whenever sign bit is 1, you have to consider respective position weight minus. That's all. Whenever sign bit is 0, the overall number is giving positive number. Okay. In this way, you can calculate the equivalent value whenever any number represented in 2's complement form. Okay. Now let us see the range of numbers. So first we'll consider, see here we are considering for n bits. If you are having n bits, what is the range of the numbers we are going to get? Okay. First let us consider for unsigned. See, when you are having n bits, total number of combinations you will get 2 power n. Okay. Since we are starting from 0, the maximal you can represent is 2 power n minus 1. Okay. Suppose if you consider n value 4, then in that case you will get 0 to 2 power 4 minus 1. So that means you will get 0 to 2 power 4 is nothing but 16. 16 minus 1 is 15. 0 to 15 you are getting 16 values. All are by default positive. But we are not representing positive sign. That's all. Next, regarding sign magnitude or 1's complement, the range remains same. Regarding sign magnitude form or 1's complement form, the range will be remain same. See, when you're having sign magnitude form, okay, whenever you're having n bits, yes, very good, Abhilash, very good. Whenever you're having n bits, okay, in the sign magnitude form, only 1 bit we are reserving for sign. The remaining n minus 1 bits, we are reserving for magnitude, right? So when you're having n bits, the max value got is 2 power n minus 1. But here, with the help of n minus 1 bits, what is the max value you are going to get? In the place of n, just substitute n minus 1. In the place of n, just substitute n minus 1. That's all. Okay. So that is a positive maximum you will get. Similarly, negative maximum you will get. Positive maximum and negative maximum. Right. Suppose if you consider n value is 4. N value 4. Just substitute here. 4 minus 1 is 3. So 2 cube is nothing but 8. 8 minus 1 is 7. So minus 7 to plus 7 you will get. If you are using 4 bits in the sign magnitude form or 1's complement form, you will get the range as minus 7 to plus 7. Minus 7 to plus 7. Similarly, if you consider 2's complement form, for n bit case, regarding positive maximum, it will remain same. But regarding negative maximum, that is nothing but minimum value. Yes, very good, Abhilash, very good. Regarding minimum value, you will get minus of 2 power n minus 1. You won't get this minus 1. Now, if you consider n value 4, just substitute here. 4 minus 1 is nothing but 3. So 2 cube is nothing but 8. So minus 8 to plus 7. Now, just observe this range and this range. What is your observation? All of you please respond. Just observe this range and this range. What is your observation point for 4-bit case? See here, regarding positive number maximum value it is same, but regarding negative maximum you are having minus 7 only, but here you are able to get up to minus 8, right? Yes, one extra number you are able to get, right? Yes. See, when you are having 4 bits, 1000, if this is represented in 2's complement form. Yes, very good Amol, very good. Okay, so here 1000 you are having, so this equivalent value is nothing but, so just place the position weights in powers of 2. Since sign bit is 1, corresponding position weight is minus, right? So minus 8 plus 0 is nothing but minus 8. So that means with the help of 4 bits, the negative maximum you can represent is minus 8. But you cannot represent plus 8 with the help of 4 bits in 2's complement form. For representing plus 8, we require 5 bits. Okay, right. But here, if you observe, in the 2's complement form, we are having unique representation for 0. Whereas in sign magnitude form and 1's complement form, we are having 2 different representations. For plus 0, we are having 1 representation. For minus 0, we are having another representation. Okay. But whereas for 2's complement form, we are having unique representation. Because of that, we are getting one negative number extra. Okay. So this is one reason why we will use 2's complement when compared to other 2 forms. Because whenever you are doing any mathematical operations in our daily life, in general, we will consider both plus 0 and minus 0 as 0 only. But if you are using sign magnitude or 1's complement, for plus 0, you are having one representation. For minus 0, you are having other representation. Okay. But in 2's complement form, you are having only one representation. That means all the bits will be zeros. Okay. Whether it is plus 0 or minus 0. Okay. Right. This is one reason why we are using 2's complement when compared to other 2. And one more reason, whenever you want to perform subtraction operation. Okay, even earlier also we have seen one case. Okay, suppose if you are using sign magnitude form, you can perform a minus b as long as a is greater than or equal to b. Because as long as a is greater than or equal to b, b is a smaller, a is the larger. So you can perform direct subtraction. But if a is less than b, that time You cannot perform direct subtraction because B is the larger when compared to A. That time what you will do? You will take minus as common, then you will get B minus A. Now in this case, A is becoming smaller when compared to B. You can perform subtraction. After that, resultant value you are getting minus. Okay, so this kind of, whether A is greater than or equal to B or A is less than B, this condition you have to check. This condition you have to check whenever you are supposed to perform subtraction. Okay, if you are using sign magnitude form. Okay, but if you are using 2's complement, if you are using 2's complement, A minus B, we can write it as A plus of minus B. Now this minus B we can write it as 2's complement of B. This minus B we can write it as 2's complement of B. So that means if you are performing 2's complement for of a number B, that is nothing but minus B. Now if you consider A is one number and this entire number 2's complement of B is something like another number Y. Okay, now you are having one adder circuit, you are giving one number as A, another number as Y, but surprisingly, the resultant value will get A minus B. That is the beauty of 2's complement method. Inside hardware circuit, you can have adder circuit only, but the resultant value will get subtraction output. But here you have to perform comparison operation, right? So this is the beauty of 2's complement. That's why these are the two reasons why we will recommend 2's complement when compared to other two. Okay, I hope it is clear for everyone the significance of 2's complement method when compared to other two. Now, say for example, if you are having one number like this, now tell me, I am writing two numbers here. If these two numbers are represented in 2's complement form, what is the corresponding decimal equivalent you are going to get? All of you just give a try. I am telling these two numbers are represented in 2's complement form. What is the equivalent decimal value for both the numbers? Yes, very good, Hemant Krishna, minus 4. Yes, very good. See, it is very simple. Just you have to place the position weights in powers of 2, 2 power 0, 2 power 1, 2 square, 2 cube. Since sign bit is 1, corresponding position weight is minus. So here, wherever ones are there, just add respective position weights. Minus 8 plus 4 is nothing but minus 4. Similarly here, the position weights are 2 power 0, 2 power 1, 2 square. Since sign bit is 1, corresponding position weight is minus. Right? Yes, very good, Anand. So minus 4 only you are getting. So that means, what is your observation just by looking at these two numbers? When you are having 3 bits 100, this number, if it is represented in 2's complement form, the equivalent decimal number you are getting minus 4. Right? The same number 100 only. If you observe, same number 100 I have copied as it is. Now here in this case, sign bit is 1. Sign bit is 1. That I have placed one more time to the left of it. Okay, the equivalent value will remain same. That means when you want, based on the requirement, okay, whenever you are having 8 number, sign bit will be 1. You can place n number of times to the left of it, the same 1, the equivalent value won't change. Similarly for positive number, I hope it is clear for everyone. For positive number, the starting bit you will be having 0. The leftmost bit you will be having 0. So you can place the same 0 n number of times to the left of it, the equivalent value won't change. Okay. Regarding positive number, there is no confusion for anyone. So the same logic will applicable for net number. Whenever net number you are having, sign bit is 1. The same 1 you can place n number of times to the left of it, the equivalent value won't change. That is called sign extension property. Sign extension property. Okay. Next, see, whenever you are performing addition of two numbers, which are represented in 2's complement form, whenever you are performing addition of two numbers which are represented in 2's complement form, okay, so that time you have to observe the sign bits. Okay. So here if you observe, you are having both are sign bits are 0. That means when you are performing addition, resultant value also you should get positive. Positive. Suppose the moment if you are getting 1 here, suppose if you are getting 1 here after performing addition of these two numbers, that means it indicates what? Overflow occurs. See, when you are performing addition of two numbers, the resultant value should be positive. Positive, right? So to overcome that drawback, we will consider one more bit. Whenever you are getting 1 here, whenever you are getting 1 here, that time we will consider one more bit. So that bit we will put 0, so that the resultant value you will get positive number only. Positive number only. Okay. Similarly, whenever you are performing addition of two numbers which are represented in two's complement form, if both the numbers are negative, that time if you are getting 0 here, suppose, that means you are performing addition of two negative numbers, but you are getting resultant value 0. That means the moment sign bit, just if you are observing sign bit, it indicates positive number, right? But that is wrong. So in this case, you have to consider one more bit. So that bit you have to consider 1, because when you are performing addition of two negative numbers, the resultant value should be negative. Whenever you are performing addition of two positive numbers, the resultant value should be positive. Okay. In order to, whenever overflow occurs, overflow can possible whenever you are adding two positive numbers or two negative numbers. Okay. But suppose if you are adding two numbers which are represented in two's complement form, okay, you are performing addition. Now in this case, after performing the addition here, okay, after performing the addition here, suppose if you are getting final carry 1, suppose after performing the addition of two 4-bit numbers, okay, in one case sign bit is 0, another case sign bit is 1. Now can you tell whether I have to consider this 1 or not into the final result? Suppose if I am getting 1 here, whether I have to consider that 1 or not? All of you please respond. Here I am assuming that all the numbers are represented in two's complement form only. Yes, very good, Hemant, very good. See, whenever you are adding two positive numbers or two negative numbers, that time there is a possibility of overflow. That means whatever the number of bits you have considered, that may not sufficient in few cases, right? Just like we started with the case carry, okay, whenever you are performing addition of two single digits, right? But here if you observe, whenever you are adding one positive number with negative number, that means actually you are performing what? Subtraction operation. Actually it is like a plus of minus b, yes or no? You are adding one positive number with negative number, that means actually you are performing subtraction. Whenever you are performing subtraction, there is no question of overflow. That means whatever the carry here, if at all you are getting, you can ignore that carry. That means whatever the number of bits you are having, with the help of that number of bits, you can represent a minus b also. Okay. So this is very important conclusion point. This is very important. Whenever in the GATE exam, if they give two numbers, like both the numbers are represented in two's complement form, but that time if you are performing addition, just you have to observe the sign bit. If the sign bits are opposite, that time if any carry comes like that, so that means the final carry you can ignore. But whenever sign bits are same, that time if any carry come, I will consider like this. Say for example, if you are getting last stage carrier as 1, I will consider that one. But here if you are getting 1, but that last stage carry you can ignore, because here overflow won't occur. I hope it is clear for everyone. So with this we have completed the first part of the first chapter, that is regarding number systems. Okay. So now let us see regarding the binary codes. So binary codes we can classify into two types. First one is alphanumeric codes. And the second one is numeric codes. Okay. See here you are having one code. Code means what? You are using some pattern of symbols, right? But here we are using the term binary. That means that symbols are nothing but in the combination of zeros and ones, right? So you are having some pattern of zeros and ones. That particular code, if you are using for representing both alphabets and numbers, then we will call that particular binary code as alphanumeric code. right? So can we say that hexadecimal number system is an example for this one? All of you please respond. Whether hexadecimal number system will come under this category? Yeah, some of you will say it is yes. Okay, if you are saying yes, then I will ask immediately one question. What is the hexadecimal code for the letter Z? What is the hexadecimal code for the letter Z? See, here what I have told, we are using the combination of ones and zeros for representing what? For representing alphabets and for representing numbers. Okay, see here in the hexadecimal number system, what happened? For a single digit, we cannot represent the values ranging from 10 to 15, right? So for represent 10 to 15, I have used the alphabets, but here we are using binary code for representing the alphabets and numbers, right? So that means hexadecimal number system won't come under this category. Now, so from your keyboard, whenever you are pressing any key, okay, internally there will be 7-bit code that is called ASCII code. So ASCII code is an example for alphanumeric code. Okay, you are having capital letters, you are having small letters, you are having digits and special characters, etc. Right? So whereas if you are using binary code only for represent numbers, then we will call it as numeric code. Okay, numeric codes we can classify further into two types. One is weighted code, another one is non-weighted code. Weighted code and non-weighted code, or you can say unweighted code, both are same. Non-weighted or unweighted code. So here, as the name implies, you are having positional weights. If you are having positional weights, then we will call it as weighted code. Yes, very good, Hemant, very good. If you are having positional weights, then we will call that particular numeric code as weighted code. If we don't have any positional weights, then we will call that code as non-weighted code or unweighted code. Okay. So can you give example for weighted and can you give example for non-weighted? I hope all of you are familiar. Yeah, Abhilash, BCD will come under first category. Yes, Amol, very good. Yeah, BCD code will come under weighted code. BCD is nothing but binary coded decimal. Binary coded decimal. Okay. So here we are using binary code for representing the decimal digits. We are using the binary code for representing the decimal digits. So that means when you're having the decimal digit, the maximal you can represent 9. The maximal you can represent 9. Yes, very good, Hemant, Amol. Yes, very good. When you're having the decimal digit, the maximal you can represent is 9, right? So for representing 9, we require 4 bits. 1001 is nothing but 9, right? So for representing 9, we require 4 bits. So that means when you're having single decimal digit, you're having 10 possible values 0 to 9. Since for representing max value, we require 4 bits. Obviously, with the help of 4 bits, we can represent any lower digit 0 to 8. Any digit we can represent with the help of 4 bits. That means it is mandatory to represent each and every decimal digit with the help of 4 bits in the BCD code. In the BCD code, it's must and should. In BCD code, for representing each and every decimal digit, we have to use 4 bits. Okay. So when you are having 4 bits, in general, you will write the positional weights like this: 2 power 0, 2 power 1, 2 square, 2 cube, right? When you convert these positional weights into the normal value, you will get 2 power 0 is nothing but 1, 2 power 1 is nothing but 2, 2 square is nothing but 4, 2 cube is nothing but 8, right? So that means 8421 code. So the other name for BCD code is 8421 code. You are having 4 positional weights. The corresponding weights are 8421. Okay. But we are using this code only for representing decimal numbers. That means since you are having only 10 possible values 0 to 9 for a single decimal digit. Okay, so the corresponding BCD code you will get like 4 zeros, 0001 and so on up to 1001. Okay, so these are the valid BCD code. Because you are having 10 possible decimal digits, for each and every digit we can represent with the help of 4 bits. But in general, whenever you are having 4 bits, totally you will get 16 combinations, but out of which we are using 10 combinations only. We are using 10 combinations. That means the remaining 6 combinations like 1010, 1011 and so on up to 4 ones. Here you will be having 6 combinations. These are non-valid BCD. These are non-valid BCD. Because we don't have other 6 combinations, right? We are having only 10 possible combinations. So for those 10 combinations, we are using the binary code. Since we are using binary code only for decimal digit, so according to the name, binary coded decimal, BCD, right? Suppose if you want to represent 10, in BCD code, okay, for representing each and every digit, we require 4 bits, okay. So that means 1 is nothing but 0001 and 0 is nothing but 4 zeros, okay. So in this way, whenever you are doing the grouping of 4 bits, you can directly write the corresponding decimal equivalent, okay, right. Now coming to the non-weighted code or unweighted code, here the examples are XS3 code and gray code. So these two are the examples of unweighted code. So XS3 code, as the name implies, 3 already has been included. See, this code also we are using for decimal digits only. We are using XS3 code. Okay. So that means for 0, if you want to represent XS3, you have to add 3. So 0 plus 3 is nothing but 3. So the corresponding code is 0011. Next, 1 plus 3 is 4. That is nothing but 0100. So in this way you will get, for 9 is nothing but 9 plus 3. That is nothing but 12. So 1100. Okay. See, if you are having decimal digit, by adding 3, you are getting the corresponding code, that is nothing but XS3. Suppose if they mention that one number 1100, if they mention that this number is represented in XS3 form, okay, if you want to write the corresponding decimal, what you have to do? 1100 is nothing but 12. You have to subtract 3 from here. So from there you will get 9. 12 minus 3 is nothing but 9. Forward approach is you have to add 3. Backward approach or reverse approach is nothing but you have to subtract 3 from there. Correct? Yes, very good, Abhilash, very good. So in this way, regarding XS3 also, if you observe, here also we are using 4 bits. But here also we are using XS3 only for the decimal digits. Okay, that means we are using only 10 combinations. Okay, so other 6 combinations are not valid XS3. So here initially you will be having 3. And here you will be having 3. So those combinations are 4 zeros, 0001, 0010. Okay, so these are the 3 combinations initially you will be having when you write the bits. Okay, and here when you continue further, you will get 3 more combinations: 1101, 1110, 4 ones. So these are non-valid XS3. Just like for BCD, similarly here non-valid XS3. Okay. Yeah, Amol, other codes are not important for GATE exam. Yeah, you will be having similar to 8421, you will be having other weighted codes. Yeah. So whatever the positional weights you have mentioned, by adding 9, by adding those positional weights, you will get 9. Okay, right. So those codes are not important for the GATE exam. Next one is gray code. See, whatever the BCD code and XS3 code we have discussed, these two are the examples of sequential code. These two are the examples for sequential code. Sequential code means, see, if you observe, when you write the code here in a sequence, okay, by adding 1 to the previous one, you will get the next code. By adding 1 to the previous code, you will get next code. Or whenever you consider any 2 successive codes, just consider the difference. That means subtract smaller from larger, you will get difference as well. Okay, because this BCD code and XS3 code we are writing for decimal digits because decimal digits follow a sequence, right? So that means these two codes are examples for sequential code, whereas gray code is not a sequential code. Can you guess gray code is an example for which code? All of you please respond. Gray code is an example for which code? XS3 and BCD codes are the examples for sequential, but gray code is not example for sequential. Can you guess? Gray code is an example for which code? Yeah, already we have mentioned it is unweighted, but I am looking for some special name. Okay, right, no issue. It is the example for unit distance code. Unit distance code. Okay, whatever the code here you are arranging in such a way that if you observe any two successive codes, only one bit position only will differ. That is, so accordingly the name unit distance code. Only one bit will change while you are placing the code in a sequence, right? That is called unit distance code. So for this example is gray code. Gray code. So here let us see regarding binary to gray code conversion and gray to binary conversion. Binary to gray and gray to binary. Binary to gray and gray to binary. See here you no need to remember any formula. Just with the help of these RTHs, you can do the conversion of binary to gray and gray to binary. Suppose I am considering binary number here. Okay, so B3, B2, B1, B0. Okay, here we are having binary code. Now I want to convert into gray code. See, whatever may be the number of bits, the procedure will remain same. Okay, so if you want to convert this binary into gray, okay, so the leftmost bit you can copy as it is. That is your the leftmost bit corresponding to gray code. Okay, so G3 and then perform XOR operation here. So then you will get the next bit, that is your G2. Perform XOR operation on successive bits like this. Then you will get the corresponding gray code bits. That's all. Okay, no need to remember any formula. Okay, similarly if you are having gray code, for easy understanding I am considering 4 bits, but the procedure will applicable for any number of bits. Okay, so here also we'll copy the starting bit as it is, that is nothing but your B3. Okay, and here see binary to gray or gray to binary, the starting step will remain same. First step is same, but the second step will change. Regarding binary to gray, we are performing XOR operation on successive bits, whereas here we will perform like this. Okay, so here we'll perform XOR operation like this. We'll get the corresponding binary bits. Okay, so for easy understanding, let us consider one number. Suppose I am considering here 1011. 1011 is the binary. So all of you with the help of this RTHR try to convert into corresponding gray. All of you do it with the help of this RTHR. No need to write any equation. Equation is not required at all. Just follow this RTHR. Yes, very good Hemant, very good. Yes, very good Naru Gopal, very good. See here, the first step will remain same. That means the MSB or starting bit, leftmost bit will copy as it is. After that, we'll perform XOR operation. 1 XOR 0 is 1, 0 XOR 1 is 1, 1 XOR 1 is 0. Okay, So if you are having binary code as 1011, the corresponding gray code as 1110. Okay, right. Very good, Abhilash. Now let us consider the same gray code here. 1110 just now we got. Now consider this is the gray code. This is the gray code. Now let us see whether we are getting the same binary code or not with the help of this architecture. Copy the first bit as it is, that is 1. Now in this case, we have to perform XOR operation like this. 1 XOR 1, that is 0. 0 XOR 1, that is 1. 1 XOR 0, that is 1. So this is the binary code. Yes, we have assumed 1011 initially. Yes, we are getting the same thing, right? So in this way, you can do binary to gray or gray to binary. Okay. And here regarding gray code, for 2-bit case, I will discuss. When you are having 2 bits, the corresponding gray code is 00, 01, 11, 10. Okay. Now if you observe here, 0 to 1, only 1 bit is changing. Here 0 to 1, 1 bit is changing. Here 1 to 0, 1 bit is changing, right? Whatever the code here we have placed, if you observe any 2 successive codes, only 1 bit is changing. So because of that, we are calling this is the unit distance code. And surprisingly, even if you observe this, after this one, if you write this starting code, suppose after 10, if you write this 00, and here if you observe, only 1 bit is changing. 10, only 1 bit is changing, right? This property will applicable even if you consider 3 bits, 4 bits, whatever may the number of bits regarding gray code. Even the first and last code also differed by only 1 bit, right? So it is called what? Cyclic code, right? So that's why we can say gray code is an example for cyclic code also. Gray code is an example for cyclic code also. According to unit distance code, whatever the codes you are arranging, okay, successive codes, any 2 successive codes if you consider, only 1 bit will differ. And according to cyclic code, even first and last, even if you are arranging, there also only 1 bit will change. Yes, very good Hemant, very good Amol. So with this we have completed regarding first chapter. So now let us proceed to the second chapter. Chapter 2, Boolean algebra and K-maps. So whenever you want to do any simplification, yes Tamlan, I will cover all the topics. Okay. So whenever you want to do any simplification, so there are 2 approaches. One is Boolean algebra, rules and laws you can use. Another approach is with the help of K-maps. Okay, right. So first let us see regarding Boolean algebra and then we'll see regarding K-maps. So first let us see the basic rules of Boolean algebra. For the timing, I am considering one variable is x. Other variable could be x or x bar, or constants are 0 and 1. 0 and 1. Okay. So first I will perform logical and I will consider one variable as x. Other variable could be one among these 4. Okay. So x into x is nothing but x. X into x bar is 0. X into 0 is 0. X into 1 is x. Similarly, I will perform logical OR. For these 4 cases, I will perform logical OR. Now, x plus x is nothing but x. It is a logical OR operator. This is the logical AND operator. This is the logical OR operator. Okay, x plus x bar is nothing but 1. X plus 0 is nothing but x. Now, can you tell what is the value here you are going to get? X plus 1 is nothing but, all of you respond. Yes, very good, Abhilash, Anand, Amol. Yes, very good. It is the logical OR operator. Whether you are considering x value 0 or 1, irrespective of that, 1 plus anything is 1. It is the logical OR operator. Right? Okay. So, just observe these arrow marks and tell me what is your observation. Just observe these arrow marks, either from left to right or you can observe from right to left also. What is your observation point? Yes, very good, Sachidanand. See, wherever logical AND is there, wherever logical AND operator is there, we have replaced with logical OR. Wherever logical AND is there, we have replaced with logical OR. Okay. And similarly, wherever zeros are there, we have replaced with 1. And similarly, wherever ones are there, we have replaced with zeros. Okay. Right. So that means what is this particular principle? Any idea? In any Boolean function, if you are interchanging logical AND with logical OR, if you are interchanging zeros and ones, what is the corresponding function you are going to get? No, not complement. These are dual. These are dual. This is the duality principle. This is the duality principle. By interchanging logical AND and logical OR, by interchanging zeros and ones, we are getting the corresponding dual function. Hi Karthik, good evening. Yes, very good Abhilash, very good. Okay, this is the duality principle. So that means whatever the arrow marks here I have represented, those are dual to each other. Okay, right. Now let us see the laws of Boolean algebra. So first one is commutative law. First one is commutative law. Here I am considering two variables. Okay. So whenever you want to perform any operation among two variables x and y, even if you are getting the same operation, even if you are interchanging the order of the variables, if you are getting the same functionality, then we will say that that operator is satisfying commutative law. So x and y is same as y and x, right? So the dual of this one is x plus y is equal to y plus x. So that means both logical AND operator, logical OR operator satisfies commutative law. So that means you can interchange the order of the variables. There is no issue at all. Next one is associative law. Next one is associative law. So here I am considering three variables. Okay. Here I am considering three variables. So first I am performing x and y and then with z, which is same as you can perform among y and z first and then with x. Okay. So that means whenever you want to perform any operation on three variables, you can perform on any two variables first and then with third variable. If like that, if it is satisfying, then we can say that that operator is satisfying associative law, right? Similarly, if you apply dual, you will get x plus y plus z is equal to x plus y plus z. Okay. So up to here we have considered left hand side equation. If you observe, I have considered only logical AND. Here I have considered only logical OR. Okay. Even if you observe the previous slide also, logical AND logical OR. Okay. Now let us consider both. Next one is distributive law. Distributive law. So here I am considering both the operators x and y plus z is equal to multiply these two, that's all, right? X and y plus x and z. So just apply dual to this one. You will get x plus yz, Wherever logical AND is there, replace with logical OR. Wherever logical OR is there, replace with logical AND. That is equal to, you can write like this, x plus y into x plus z. X plus y into x plus z. See, if you are having any doubt, it is very simple. Here you are having single variable, right? So you have performed logical AND with these two variables individually and then you have added, right? In the same way you can perform here. X into x is nothing but x, plus xz. Similarly, y into x is nothing but xy plus yz. From there, first three terms you can take x as common. You will get 1 plus y plus z. Y plus z value could be anything. You will get 1 plus anything is 1. So finally, you are going to get this value, right? So based on the, while you are doing the simplification, based on the requirement, if you are having the function like this, you can write like this, or if you are having the function like this, you can write like this. Okay. See, because ultimately the motto of why we are using these laws, because we want to get the simplified function, right? Suppose if you are having the function like this, by using distribute law, you can write like this, x plus y into x plus z. But suppose if you are having the function like this, just observe the common part in both the brackets. X plus is same in both the brackets. So first write that part as it is, and then you perform logical and among those two, y and z. Okay, so that one will be there. Okay, right. Similarly, if you are having a plus a bar b, so all of you please respond by using distribute law what you are going to get. Yes, very good, Naru Gopal, Abhilash. Yes, a plus a bar is nothing but 1, so you will get a plus b. You will get a plus b, right? See, here you are having single variable. Even you when you are having term also, there also it will applicable, right? So whatever the term here you are having, that entire term will come. Okay, so this is the distribute law. This is based on distribute law only. A plus a bar b is nothing but a plus b. Okay. Can you guess what is the next important and powerful law of entire Boolean algebra? Can you guess what is the most important and powerful law of entire Boolean algebra? Yes, very good, Abhilash, very good. Others also please respond. You are having one more law. Yes, very good, consensus law. Consensus law. So here you are having like this, xy plus x bar z plus yz, which is equal to xy plus x bar z. Xy plus x bar z. Similarly, you can apply dual later. Okay. So here if you observe, you are having yz. For the timing, if you consider this term, y is present in this term, z is present in this term. In this particular term, the missing variable is what? X. The missing variable is x. That is present here in normal form, and in its complement form is present here, right? So that means this term is not at all required. This term you can say it is the redundant. Even in the absence of this term, you will get the same functionality. So that means with the help of first two terms, you can get the same functionality, right? So when you are able to get the same functionality with the help of two terms, why unnecessarily the third term, right? So this is redundant term. Okay. Even in the absence of this one, you will get the same functionality. So this is called consensus law. See, regarding consensus law, you should not by heart the equation, but you should remember the two conditions regarding consensus law. Whenever you are having three terms, there is the possibility to bring to the two terms, provided whatever the two conditions we have told. Whichever term you are considering in that term, here in this example, y is present here, z is present here. Y can present here, z can present here. No problem at all. Okay. Missing variable is x. That is present normal form here, complement here. X can present here, x bar can present here. Okay. There also it will applicable. Okay. So regarding consensus law, don't by heart the equation, but remember that logic. Okay. Two logics you can remember. Okay. Right. See, whatever so far we have discussed basic rules and laws, with the help of these rules and laws, you can do the simplification of any Boolean function. Okay. But whenever you want to perform the complement of the function, that time obviously we will use De Morgan's law. So by using De Morgan's law, we can find the complement of the Boolean function, right? So xy whole bar is nothing but x bar plus y bar. Similarly, if you apply dual, you will get x plus y whole bar is nothing but x bar into y bar. See, it is very simple. Here for easy understanding, I have considered two variables, but you can have n number of variables. Even there also it will applicable. Okay. And even here, instead of a variable, you can have the term. There also it will applicable. Okay. whatever the terms you are having, so each and every term will get complement. Here if you are using logical AND, you will get logical OR. If you are using logical OR, you will get logical AND, like that. Okay. So even whenever you are supposed to find the complement also, before using De Morgan's law, you just observe the given function, whether is it possible to do the simplification or not. If there is a possibility to do the simplification, first do it. Okay. After that you can apply De Morgan's law, because ultimately your requirement what? You want to get the simplified function in easy manner, right? So unnecessarily don't increase the complexity. Wherever there is a possibility to do the simplification, first do it. After that, if De Morgan's law is required, definitely you can apply. Okay, right. So with the help of these laws, you can do the simplification of any Boolean function, and wherever complement you are supposed to find, you can use De Morgan's law. So next topic is regarding min terms, max terms and their properties. Min terms and max terms and their properties. See, min term is nothing but a logical AND term. Min term is nothing but logical AND term, or logical AND when you are performing, simply you are getting what? Product term. Simply you are getting product term. So min term is nothing but simply a logical AND term or product term, but there is one condition in which number of literals should be equal to number of given variables. Similarly, regarding max term, you will use another operator that is called logical OR. So max term is nothing but logical OR term. So whenever you are using the symbol logical OR, regarding that you will use plus symbol. So accordingly you can say that is a sum term. So here also the condition remains same, in which number of literals should be equal to number of given variables, right? Yeah, Karthik, yeah. I hope, yes, 0 plus 0 is nothing but 0 only, because it is a logical OR operator. Okay, right. So here, do you know what is literal? What is literal? Suppose in general you are having variables as A, B, C. In general we will call A, B, C are the variables. Okay, but you will be having corresponding complements also, like A bar, B bar, C bar. Okay, so that means literal is nothing but the variable either in its normal form or in its complement form, we will call them as literal, right? So all these are examples for literals. Okay, so for easy understanding, I am writing one min term here. Suppose f is a function of two variables a, b, and if you are having the term like this, a bar b. Okay, so here if you observe, you are having two literals, and among which logical AND operation we are performing, right? So the number of literals is 2, and we are performing logical AND, so we will call this one as min term, right? So if you want, you can represent this one as small m stands for min term. Here a bar b you are having, so that means a value is 0, b value is 1. When you substitute here, 0 bar is nothing but 1 into 1, that is nothing but 1. So that means the min term 1. Whatever the notation you are getting, correspond decimal equivalent you can put as a suffix, right? Similarly here, suppose f is a function of two variables. Suppose if you are having a plus b bar, suppose. Okay, so here a is normal form, so that means a value is 0, b is in complement form, so that means b value is 1. Just substitute here 0 plus 1 bar, 1 bar is nothing but 0, 0 plus 0 is nothing but 0, right? So here you are getting logical OR term in which number of literals equal to 2, that is same as number of given variables, so we will call it as max term. max term we will represent with the letter capital M, and 0, 1 is nothing but 1. 0, 1 is nothing but 1, right? So what is your observation? Here I have written small m1, here I have written capital M1. Don't tell that here small letter, here capital letter. What is your observation when you observe A bar B and A plus B bar? Yeah, not dual. These two are complement. These two are complement. See, M1 if you write A bar B, if you apply complement by using De Morgan's law, each and every term will get complement. A bar whole bar is nothing but A plus B bar, right? So M1 and small m1 and capital M1, those two are complement to each other. Those two are complement to each other. Okay. So this is the first property. Min terms and max terms are complement to each other. Min terms and max terms are complement to each other. So if you want, you can write like this. Min term we will represent as small mi, which is equal to complement of max term, or you can write max term is complement of min term, vice versa. And if you are having n Boolean variables, then you will be having 2 power n min terms, and similarly you can get 2 power n max terms. If you are having n Boolean variables, you will be having 2 power n min terms, similarly 2 power n max terms, right? Now let us see the properties of min terms. Properties of min terms, and similarly we'll write the corresponding properties of max terms. So I hope all of you know the properties of min term. The first property is sum of all min terms is equal to 1. So since we are starting from 0, the max value will be 2 power n minus 1 regarding I. So when you add all the min terms, you will get 1. Okay. So the corresponding property here you will get, here sigma stands for sum. The corresponding another function you will get pi. Pi stands for product. Range will remain same. I equal to 0 to 2 power n minus 1. Here min terms I have used, here max terms. Now here you are having 1, the corresponding you will get 0. So that means sum of all min terms equal to 1, product of all max terms is equal to 0, right? And then if you are performing multiplication of two min terms, mi and mj, if I and j are not equal, that means m1 m2 or m2 m3 like that. Okay. If you are performing multiplication, you will get 0. Suppose if j equal to I, so in the place of j you can consider I. It is like mi into mi, just like x into x is nothing but x. Okay, in the same way here you will get the same min term, right? Similarly here, when you add two max terms, if I and j are not equal, then you will get 1. If I and j are not equal, then you will get 1. If j equal to I, then you will get the same max term. Just in the place of j, if you consider I, x plus x is nothing but x, right? In the same way. So mostly you will use these properties of min terms while you are doing the simplification of the Boolean functions with the help of logic gates, or whenever you are having two functions which are represented in sigma m form. Okay, if you are supposed to multiply, that time these properties of min terms will be applicable. Similarly, whenever you are having product of max terms form, that time you can use these properties. Next one, algebraic expressions. Algebraic expressions for Boolean functions. Algebraic expressions for Boolean functions. See, in general, whenever you are having truth table, from the truth table you will get one of these two forms. First one is sum of minterms form, or you can write the same output variable, you can write in another form, that is product of maxterms form. Sum of minterms form or product of maxterms form. Say for example, for easy understanding, I am considering the truth table of one logic function. Okay, say for example, I am writing like this: 0 1 1 0. Okay, right. So here, if you observe, for 0 1 combination, 1 0 combination, we are getting output as 1. So for whichever input combinations we are getting output as 1, that means the corresponding input combinations are nothing but minterms. Here M1, M2. 0 1 is nothing but 1, 1 0 is nothing but 2. Okay, when you're having 0 1 combination, you're getting 1, or when you're having 1 0 combination, also you're having 1, right? So that means now you can represent y. By considering these two minterms, right? So you can write y equal to m1 plus m2. So regarding sum, you can use the symbol sigma. Small m stands for minterm, and here the numbers are 1 2. You can represent like this also. Or if you want to write the minterms in terms of the variables, you can write 0 1 combination. That means a bar b plus m2 is nothing but 1 0. So that means ab bar. I hope all of you are familiar. The given truth table is nothing but what? XOR truth table. A XOR B. Right. So here if you observe, you are having two product terms. In each product term, number of literals equal to 2. It is same as the number of given variables, right? So since minterms are summed together, it is the sum of minterms, right? Say for example, some of you are saying that for these two input combinations, we are getting output as 1. That means the other students can say that for other combination of inputs, we are getting output as 0, right? For other combination of inputs, we are getting output as 0. That means for whichever combination of inputs, if you are getting output as 0, the input combinations are nothing but what? Maxterms. The corresponding input combinations are nothing but maxterms, right? So now you can use this form, product of maxterms. So that means y equal to m0 into m3. Product is nothing but, we can use the symbol pi. Capital M stands for maxterm. The terms are 0 3. Now write m0 m3 in terms of the variables. Here 0 0. That means you will write a plus b. Here 1 1. That means a bar plus b bar. See, if you are having any doubt, just substitute this combination. 0 plus 0 is nothing but 0. Next, 1 bar plus 1 bar is nothing but 0. Like that. See, whatever the notation we are following for minterms, exactly opposite we have to follow for maxterm. Okay. Here whenever value is 1, normal form. But here whenever value is 1, complement version. Here whenever value is 0, complement version. But here whenever value is 0, normal version. Like that. Okay. Now all of you please respond. This equation and this equation, whether both are same or different, after doing further simplification. How many of you are saying this equation both are equivalent? How many of you are not agreeing? Yes, very good, Amol, Anand. Yes. See, ultimately what? See, from the truth table, whatever the number of input combinations you might be having, okay, at the output side, you will get either 0 for few combination of inputs, you may get for other combination of inputs 1, right? So some of you, if you are saying that for few combination of inputs, if I am getting output as 1, the other students can say that for remaining combination of inputs, I am getting 0. Ultimately, you are representing the same function only. That means here if you observe, a into a bar is nothing but 0, a into b bar, that means you are getting this term. Next, b into a bar we can write as a bar b by using commutative law, that means you are getting this term. And then b into b bar is nothing but 0. So whenever you are having the truth table, from the truth table, whatever the output variables you are having, each and every output variable, either you can represent sigma m form or you can represent pi capital M form. Okay. So in general, after doing the simplification of sigma m, you will get sum of products form. That means SOP. In short, we can call it as SOP. Sum of products form or SOP. Similarly, if you are simplifying pi capital M, you will get POS form. That means product of sums form. Okay, for easy understanding, I am writing some random example, arbitrary example. Suppose if f is a function of 5 variables, after doing some simplification, I got like this: a bar c plus b into d bar u. Okay, now if you observe these two terms, individually those are product terms, but the number of literals here present is here 2, here 3, but the total number of variables are 5. Since both are not matching, we will call simply product terms. These product terms are summed together, so that's why it is sum of products, right? So in a similar way, here regarding POS form, f is a function of 5 variables. I am writing some random example: a plus b into c plus d plus e bar. Here also, if you observe one sum term, another sum term, these two are product together, hence it is POS. Okay. In general, after doing the simplification of sigma m, you will get SOP. Similarly, after doing simplification of pi capital M, you will get POS. Okay. So whenever we are having sigma m, we can convert into pi capital M. Similarly, pi capital M into sigma m. Okay, so in this way, with the help of basic rules and laws, whenever you're having the function in the sigma m, after doing simplification, you will get SOP. Similarly, if you're having the function like this, you will get POS. Similarly, if you want, you can do the conversion opposite way also. Okay, so this is about Boolean algebra. Now let us see regarding K-maps. So I am considering one simple example. F is a function of 3 variables, x, y, z, which is equal to sigma m 1367. All of you just draw the K-map and try to find out how many prime implicants are there, how many essential prime implicants are there, how many redundant prime implicants are there. All of you give a try. For easy understanding, I have considered one question with the help of 3 variable, another question with the help of 4 variable. Yes, very good Naru Gopal, very good Anant. Yes, very good. See, first step is whenever you're having Boolean function, okay, if you want to calculate regarding number of prime implicants, essential and redundant prime implicants, etc. Regarding prime implicants, obviously you have to draw the K-map, right? So first step is you have to place the ones in the respective minterm positions. Here the minterms are 1, 3, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. So this is the first step. In the respective minterm positions, you can place the ones. Okay, regarding minterm, just now we have told for those input combinations you are getting output as 1, right? So after that what you have to do? You have to do the grouping of adjacently placed ones in decreasing powers of 2. Since it is a 3 variable function, first you will check whether grouping of 2 power 3 adjacently placed ones is possible or not. In the given function itself, you are having 4 minterms. There is no question of grouping of 8 adjacently placed ones. You can eliminate that one. Then go for 2 square. Grouping of 4 adjacently placed ones. Here you are having 4 ones. See, if you are having 1 here, you can do the grouping of 4 ones. Or if you are having 2 ones here, we can do the grouping of 4 ones like this. Or if you are having this one here, we can do the grouping of 4 ones. Here in this K-map, you are having 4 ones, but all the 4 ones together not adjacent, right? So this is also not possible. Then go for 2 power 1. Yes, in this case it is possible. So you can do all the possible groupings of 2 power 1 adjacently placed ones, right? So you can do grouping of these 2 ones, and you can do grouping of these 2 ones, and then you can do grouping of these 2 ones. So like that, 3 possible groupings are there. After that, there is no one left over, then you no need to go for grouping of 2 power 0. But in this way, you have to start from highest power to the least power. Okay, right. So here we are getting 3 groupings. From each grouping you will get one product term. Just observe this grouping. Row wise x value is 0, that means x bar. Column wise z value is 1, that means z. X bar z you are getting. Similarly, regarding this grouping, row wise x value is 1, and column wise y value is 1, y. Okay, right. And regarding this column grouping, if you observe, y value, z value equal to 1, so you will get yz. Now, see, whenever you are doing the groupings, you have to observe row wise and column wise, whichever values are constant, accordingly you will get the term. Whichever variable values are changing, that is getting minimization. Okay, in the minimization process, it is getting eliminated because of this gray code. Okay, I have already told gray code property is what? Whatever the bits, whatever the code you are placing successively, only one bit is changing, right? So that particular variable is getting minimized. Okay, that is called adjacency property, right? So that is the beauty of K-map. With the help of K-map, we can do the simplification easily. Okay, now from each grouping, whatever the product terms we are getting, initially I will call them as prime implicant. After that, I will check whether that particular grouping is compulsory or not. If the grouping is compulsory, we can rename that prime implicant as essential prime implicant. See, if you observe this particular green color grouping, okay, for the timing, if you remove this grouping, for this one, whether we are having any other grouping? No. That means this grouping is compulsory. So whenever compulsory grouping, we will call that product term as essential prime implicant. Similarly, if you observe this grouping with respect to this one, okay, if you don't do this grouping, there is no other grouping. So that means this is also essential. Now, if you observe this column grouping, even if you don't do this grouping, this one was covered by some other grouping, this one was covered by some other grouping. So simply we will call it as prime implicant. So initially, when you have drawn the K-map for the given function, you are getting the number of prime implicants are 3. Initially, you are getting number of prime implicants are 3, out of which you are getting 2 are the essential and 1 simply I am calling as prime implicant. Now let us write the minimized function. In the minimized function, first we will write essential prime implicants compulsory. After that, if any prime implicants are required, that we will consider. Otherwise, it is optional. optional. Okay, so for this question you are having two essential prime implicants. So f of xyz is equal to x bar z plus xy. Now let us see whether this prime implicant is required or not. Okay, right, just observe. With the help of this grouping we have covered these two ones, and similarly with the help of this grouping we have covered these two ones. So for this K map you are having total 4 ones. All the 4 ones we are able to cover with the help of these two essential prime implicants. That means this one is not required. So that means now you can say this prime implicant as redundant prime implicant. Okay, see, if you write all the 3 terms, what you are going to get here, just I am writing, if you are having all the 3 terms, all the 3 groupings, what you are going to get, x bar z plus yz plus xy. See, I have asked the question to find regarding prime implicants, essential redundant prime implicants. So that's why you have drawn the K map. Suppose if I not asked regarding prime implicants, if I give only this function, if I ask you to simplify, then which law of Boolean algebra you will apply so that you will get this equation? All of you respond. If you are supposed to do the simplification of this one, then by using which law of Boolean algebra you will get this one? Yes, very good, Abhilash, Amol, Anant. Yes, very good. That's why I have told earlier, consensus law is the most important and powerful law of entire Boolean algebra. Okay, except with the help of consensus law, you cannot do any simplification if you are using laws of Boolean algebra. Okay, but of course, if you observe whatever the equation earlier I have written, the same equation I have considered here. Now this is the proof. By using K map, you are getting the simplified function, right? So regarding consensus law, the proof, if you want, you can do the derivation by using K map like this. Okay, right. So here for the given K map, the number of prime implicants are 3. Out of which 2 of them are essential and 1 of them is redundant prime implicant. Okay. So whatever the number of groupings you are getting in the decreasing order, okay, of adjacently placed ones like this, okay, from each grouping you are getting one product term. So that means since you are getting 3 groupings, 3 are prime implicants, out of which we have checked how many groupings are compulsory. So 2 are compulsory, this one is not compulsory. See, whenever the question is regarding prime implicant, essential, redundant, that time obviously you will use the K map and you will do the groupings. But whenever the question is regarding minimization, with the help of experience, you will do only this grouping and you will do only this grouping. You will avoid this kind of grouping, because while you are placing this kind of grouping, while visualization, you are observing that this grouping is not at all required, because these 2 are compulsory. With the help of these 2, when you are able to cover all the ones, this is not required, it is redundant, right? So whenever the question is regarding minimization, that time you can avoid doing the grouping of this. Okay, but whenever the question is regarding in terms of prime implicants, obviously you have to do all the possible groupings. I hope it is clear for everyone. Now let us see regarding this question. So for this question, how many adjacently placed ones we can do combinedly grouping? In this case, we are able to do the grouping of 2 power 1 adjacently placed ones. For this K map, how many adjacently placed ones we can do combinedly grouping? Any guess? Yes, very good, Anant, Amol. Yes, see here you are having don't care. So whichever don't care is helping in order to get the minimization, that time you can consider the don't care as 1, because we are dealing about ones. Similarly, if you are doing the groupings with the help of zeros, that time you can consider 0 like that. Okay, so here if you are considering this don't care as 1, then there is a possibility of doing grouping of 4 ones like this. Similarly, if you consider this don't care as 1, you can do grouping of 4 ones like this. And similarly, if you consider this don't care as 1, you can do grouping of 4 ones like this. And if you consider these two don't cares as 1s, then you can do the grouping of 4 ones like this. Right. So for this K map, total you are getting 4 groupings. Right. So for this grouping, the term you will get row wise p value is 0, that means p bar, and here you are getting s, p bar s. Next, regarding this grouping, q value is 1, and column wise once again s value is 1, s. Regarding this row wise grouping, p value, q value both are equal to 1. Next, regarding this grouping, here p value is 1, and column wise s value is 0, that means s bar. So for this K map, you are getting 4 groupings, all are grouping of 4 adjacently placed ones. So that means from each grouping you are getting one product term. So initially we will call all these product terms as prime implicants. Okay, all these product terms we will call it as prime implicants. Now we'll see, now just observe this K map, out of these 4 groupings, which groupings are compulsory or how many groupings are compulsory, just by observing this K map. According to the definition here I have given regarding essential, just apply the same concept there. How many essential prime implicants from observing the K map you are getting? Yes, very good Anand. Yeah, see, just by observing according to this definition, initially if you observe this grouping, here with respect to this one or this one, this grouping is compulsory, so that means it is essential. Similarly, if you observe this particular grouping, okay, with respect to this one, this grouping is mandatory, so that means it is essential. With respect to that basic sense, initially you are getting 2 essential. Okay. Now if you observe this grouping, you are having 3 ones. If you remove this grouping, these 3 ones are having, this one is having this grouping, these 2 ones are having this grouping. So it is simply prime implicant. Similarly, if you consider this grouping, you are having 3 ones. Even if you remove this grouping, this one was covered by some other grouping, these 2 ones are covered by some other grouping. So initially, with respect to the basic definition, out of 4, we are getting 2 essential. Now let us see what is the final answer regarding essential. We'll see in short. Okay. Now first write the minimized function. Same. First write essential prime implicants first. So for this function, the minimized function, I am writing essential prime implicants p bar s plus ps bar. So first one and last one are essential. P bar s, with the help of this one, we are able to cover these 3 ones. Okay. And with the help of this grouping, we are able to cover these 2 ones. See, we have to focus only once. Okay. In this case, you can ignore regarding don't case. Okay. No problem at all. Whether we are able to cover all the ones or not, that is our motto. Now, when we have considered these 2 essential prime implicants, here 3 ones, here 2 ones, together 5 ones we are able to cover, but these 2 ones, whether these 2 ones are covered by any of these 2 essential prime implicants? No. That means now this is coming into picture. Because whatever essential prime implicants you are having, with the help of those essential prime implicants, if you are not able to cover all the ones, okay, if any of the ones left over like this, in order to cover those ones, we have to consider required prime implicant. Now, according to this K map, you are having 2 possibilities. Either you can do this grouping or you can do this grouping, but not both. Yes or no? Because if you consider both, that is not the minimized function, right? So with the help of this one, that is sufficient, or with the help of this one, it is sufficient, right? So one among these 2 are required. So that means you are getting 2 possible solutions for this question. And both are equivalent minimized functions. So whichever terms are same, so that those are nothing but essential prime implicants, and whichever terms are changing, those are simply prime implicant. Okay, according to the basic definition. Okay, but in the minimized function, definitely 3 terms should be there. Yes or no? In the minimized function, 3 terms should be there. In this minimized function or in this minimized function, three prime implicants are required, right? So that means obviously among these two, one we have to consider, right? So that means with respect to that, suppose if you are considering this one, as essential, then this is the redundant. Or if you are considering this one as essential, this will be redundant, like that, vice versa. Okay, so that means for this question, total number of prime implicants are 4, out of which 3 are essential, and 1 is redundant. I hope it is clear for everyone. But among these two, 1 is required. When you are considering this one, this will be redundant, or when you are considering this one, this will be redundant, like that. Is it clear for everyone regarding prime implicants, essential prime implicants, and redundant prime implicants? Okay, I have discussed regarding 3 variable and 4 variable. Whenever, suppose here you are having, 2 ones, and here instead of 2 ones here, if you are having 2 ones here, then you will do grouping here, In that K-map, both the groupings are compulsory. So that means in the minimized function, you will be having only essential prime implicants. Okay. Whenever you are having any K-map, if simply essential prime implicants are there, obviously the minimized function will be essential. Okay. But if it is a combination of essential and prime implicant, then first we will consider essential prime implicants. After that, we will check whether it is required or not. Okay. If you are able to cover all the ones with the help of this one, this is not required. Okay. But if you are unable to cover few ones with the help of these essential prime implicants, that time in order to cover these ones, we have to consider required prime implicant. So that time I will rename that prime implicant as essential. Okay, if you are considering this one as essential, this will be redundant, or if this one is essential, that will be redundant, like that, vice versa. Okay, I hope all of you got the clarity. So with this understanding, now tell me whether, okay, I will write 2 statements here. So among these 2 statements, which one is correct? All of you please respond. Among these 2 statements, which one is correct, which one is wrong? Yes, very good Abhilash, very good Amol. Yes, very good Anand. Yes, all of you are following. Yes, very good, very good. See, the moment if you are saying one of the prime implicant is essential, by default it is a prime implicant. So this statement is correct. So all the prime implicants need not be essential always, right? So this statement is wrong. All essential prime implicants are by default prime implicants, but all prime implicants need not be essential always, right? Yes. So with this, we have completed the Boolean algebra and K-maps. Now the next chapter is logic gates. Chapter 3, logic gates implementation. So here, whatever the logic gates we are having, we can classify into 3 types. So first one is basic gates, and second one is universal gates, and third one is special gates. Whatever the logic gates we are having, we can classify them into 3 types. Okay, I hope all of you know that regarding basic gates, we are having AND gate, OR gate, and NOT gate. AND gate, OR gate, and NOT gate, these are the basic gates, because see, whatever may be the digital circuit or system you might be having, whatever might be the bigger circuit or system you might be having in terms of digital, okay, so the entire circuit you can represent in terms of what? Logical AND operator among 2 variables, or logical OR operator, or wherever you required, you can use complement. So that means by the combination of these 3 operations, you can represent any Boolean function, right? So That's why we are calling these gates are basic gates. Okay. And similarly, regarding universal gates, we are having NAND gates and NOR gates. NAND gate and NOR gate are called as universal gates because by using NAND gates alone, you can implement any Boolean function. Similarly, by using NOR gates alone, you can implement any Boolean function. Or even if you observe from the basic definition regarding basic gates, with the help of basic gates, that means by the combination of these three gates, we can implement any Boolean function. So that means if you are able to implement with the help of NAND gates, these three gates, similarly with the help of NOR gates, if you are able to implement these three gates, then also we can say that these two gates are the universal gates, right? And then regarding special gates, you are having XOR gate and XNOR gate. XOR gate and XNOR gate are called as special gates because these two gates we will use in the special applications, right? See, whenever you are transmitting the information in terms of zeros and ones, okay, sometimes few bits may be corrupted, or instead of 0 it may be received as 1, or instead of 1 it may receive as 0, right? So in order to know in which bit position error is there, and in order to correct that particular bit, we will add the parity bits along with your message bits, right? So for parity generation and parity checking regarding odd parity, even parity, accordingly we can use these gates, right? Hi Mayank, good evening. So we are having whatever the logic gates we are having, we can classify into these three types, right? I hope all of you know regarding each and every logic gate when you are going to get output as 1, when you are going to get output as 0, right? So regarding XOR gate, all of you please respond when you will get output as 1. For generalized case I am asking, when you are having 2 inputs or more than 2 inputs, okay, when you can say output is 1 based on the input combinations. For generalized case I am asking whether odd number of ones or even number of ones, for which case you are going to get output as 1. Regarding XOR gate, odd number of inputs, odd number of ones or even number of ones? Yes, very good, odd number of ones. Whenever you are having odd number of ones present at the input, that time you will get output as 1. Similarly for XNOR gate, whenever you are having even number of ones present at the input, that time you will get output as 1. See, for generalized case, see, just like AND gate and NAND gate are complement, similarly OR gate, NOR gate are complement. In the similar way, for generalized case, XOR gate and XNOR gate are complement to each other for generalized case, whether 2 inputs or more than 2 inputs. But only for 2 inputs, you will get one more relation between XOR and XNOR. Okay, I will disclose shortly. See, what is the dual of AND gate? All of you please respond. What is the dual of AND gate? Yes, obviously it is the OR gate, right? Yes, very good. Because just by applying duality principle, wherever logical AND is there, we are replacing with logical OR, right? Similarly, dual of AND gate is OR gate. Okay. Similarly, if you observe NAND gate and NOR gate, these two are dual to each other. These two are dual to each other. In a similar way, only for 2 input case, XOR gate and XNOR gate, those two also dual to each other. Whether it is dual or not, let us see. Only for 2 input case I am telling. For generalized case, these two are complement to each other. For 2 input case, these two are complement to each other as well as these two are dual to each other. Just apply dual. So just write the dual expression here, A bar plus B into A plus B bar. A plus B bar. So A bar into A is nothing but 0. A bar into B bar. Okay, you are getting A bar B bar plus B into A, you can write as AB plus B into B bar is nothing but 0. So A bar B bar plus AB is nothing but A XNOR B. A XNOR B. Only for 2 input case, XOR gate, XNOR gate, those two are dual to each other and complement to each other. But for generalized case, XOR gate and XNOR gate are complement to each other, just like AND gate, NAND gate, OR gate, NOR gate. Now tell me, with this understanding, what is the dual of this one? What is the dual of NOT gate? Yes, very good, Abhilash, very good. See, while you are performing duality principle, what we have told, we have to interchange logical and unlogical OR operators. But regarding NOT gate, you will get the output function as what? Complement of input. Okay. So this particular operator is called unary operator. You are performing complement operation on the same variable, on one variable, right? So this is called unary operator. Since you don't have any other variable, there is no question of logical and or logical OR, right? If you are having logical and or logical OR, we can interchange. But this is the unary operator. So if you are applying dual, you will get the same function. So that means the dual of NOT gate is itself only. Dual of NOT gate is same itself. Dual of NOT gate is itself. Similarly, dual of buffer is same, buffer only, like that. Yes, correct, Mayank. If you are having zeros and ones, we can interchange. But here we don't have, so that's why I have skipped that part. But earlier I have explained regarding duality in the beginning of this chapter. Yes. Okay, right. Now let us see regarding the minimum number of NAND gates. Regarding regarding minimum number of NAND gates and minimum number of NOR gates. Minimum number of NAND gates, minimum number of NOR gates required. So here I am considering all the other logic gates. So first I will consider NOT gate. So as you all know that for NOT gate, for implementation, if you connect both the inputs tied together, then 2 input NAND gate will behave as NOT gate. Similarly, 2 input NOR gate will behave as NOR gate. So we require only one gate. Okay. Similarly, next one, AND gate. For AND gate, we require 2 NAND gates. Okay. For OR gate, we require 2 NOR gates. Okay. So here we require 3, here we require 3. Okay, right. See, if you are having any doubt regarding this one, we will discuss. I hope all of you know how to implement by using NAND gates, the basic gates. Similarly, by using NOR gates, how to implement the basic gates. Okay, right. Next one is regarding XOR gate. Regarding XOR gate, with the help of NAND, we require 4. Similarly, for XNOR gate, with the help of NOR, we require 4. Now, here obviously you will get 5. See, this tabular form is applicable only when? Can you tell? Whatever the tabular form, here I have mentioned the numbers. These numbers are applicable for which case? What is the condition regarding the inputs? Yeah. So whatever the inputs we have considered, if those inputs are available, only in the normal form, if the inputs are available in only normal form, then only whatever the values here I have discussed, all those are applicable. Right? Yes, very good, Rohit. Correct. Suppose if the inputs are available in both normal and complemented forms. In the question, if they specify that if the inputs are available in both normal and complemented forms, now in this case, what will be the minimum number of NAND, minimum number of NOR? Let us see. See, regarding NOT gate, There is no change. Sorry, regarding NOT gate, can you guess what is the answer? What is the minimum number of NAND NOR required whenever both normal form and complement form are available? We don't require any logic gate, right? Yes, very good, Anand, very good. We don't require any logic gate because NOT gate is nothing but what? A bar. NOT gate is nothing but A bar. In the question it is mentioned that both the inputs normal and complement are available. So that means whenever complement version you are getting, you don't need of any logic gate. So here you are going to get 0. 0. For both the cases 0. Now coming to the AND gate. AND gate is nothing but AB. By using NAND gates, first you will get complement version. After that you require NAND based inverter, right? So obviously here you require 2. Next, regarding OR gate. First, by using NOR gate, first you will get complement version. After that complement. Okay, NOR gate output first you will get. After that NOR based inverter. So that means here also 2. It is same. Now think about these two. Regarding AND gate, how many NOR gates we require? Regarding OR gate, how many NOR gates we require? Sorry, regarding OR gate, how many NAND gates required? So just think about this number and this number. Whether is there any change or same number? In this condition, if both normal and complement inputs are available. Yeah, thank you Hemant for asking that query. So if there is any update, you will get the notification in our channel. Okay. So all of you please subscribe and click on bell icon. Okay. So that you will get instant notifications whenever upcoming videos are there, you will get the notification. Okay. So that you can attend those live sessions, you will get the benefit. Yes, very good Hemant, very good. Yes. See, if you are using by using NOR gates, so this one we can write. Sorry. So here you can apply De Morgan's law. AB bar is nothing but A bar plus B bar, and then keep external complement as it is. Okay. So in the question it is mentioned that both normal and complement inputs are available. So you don't need to generate that one. So you require only one NOR gate, right? You require only one NOR gate. Similarly here, OR gate implementation by using NAND. So apply De Morgan's law here. You will get A bar, B bar, and keep external complement as it is. Here also A bar, B bar available, so you require only one NAND gate. I hope it is clear for everyone. Yes, very good Hemant. Yes. Now regarding XOR gate, regarding XNOR gate, see whatever the tabular form here you are having 4, 5, 5, 4. Okay. See, whenever in the question if they mention that if inputs are available only normal form, so regarding XOR gate, XNOR gate, see either answer will be 4 or 5. Okay. So how to remember whether the answer is 4 or 5? So it is very simple. Here you are having the word NOR. Here also word NOR is there. Okay. NOR, both are same. So remember for one case. Okay. For one case, here NOR matching. So the answer will be 4. Just remember here. XNOR gate dual is what? XOR gate. XNOR gate dual is XOR gate. So that means NOR gate dual is NAND gate. NOR gate dual is NAND gate. Correct? So that means once if you are able to get XNOR gate with the help of NOR gates, wherever NOR is there, if you are replacing NAND, you will get XOR gate. So that means same answer. So for one case if you are getting 4, for other case it is 5. Simple. Because XOR gate if you are getting, okay, with the help of 4 NAND gates, if you want XNOR, after that you will use NAND based inverter. That's why you require 5th. Similarly, once if you are getting XNOR gate with the help of 4 NOR gates, if you want XOR gate, XNOR complement is XOR, so we require NOR based inverter, so that's why we require 5. Okay. Now, whenever they say that both the inputs normal form complement are available, for XOR gate, XNOR gate, in all these 4 cases, you will get only one answer, that is 3. So all of you give a try later. Okay. So for one case I will discuss regarding XOR gate, A bar B plus AB bar. So just apply 2 times complement, you will get the same function. For inner complement, you can use De Morgan's law. First term complement, second term complement, and keep external complement. So in the question, it is mentioned that A bar, B bar available. We no need of any logic gate. Okay. So we require 1 second. After that, assume x1, x2, and this one is x3. Similarly, you try for other. In all the 4 cases, you will get 3. So it is very important whenever you are attempting any question regarding logic gates, they will ask always regarding minimum number. But based on the context, the answer will vary. Okay, it is very, very important whenever you are answering any question regarding any subject, you should read the question carefully. Based on the context, the answer will vary. Even in the previous chapter, in the first chapter, I have mentioned regarding 2's complement representation. The wording is very, very important. Okay. Similarly, here regarding logic gates, minimum number and based on the condition. Okay. In general, if they don't mention regarding anything about the inputs, by default, normal inputs are available. By default, normal inputs are available. But sometimes they will specify that the normal inputs complemented, both are available, or the normal inputs are available and NOT gate is available. Okay. NOT gate available means the corresponding complement version is available, like that. Okay. So in this way, based on the context, the answer will vary. So you have to answer carefully. It is very, very important. So this is about logic gates. Okay. All the logic gates with the help of NAND and NOR. Okay. In general, as I mentioned earlier, with the help of NAND, we can implement any Boolean function. Similarly, with the help of NOR, we can implement any Boolean function, right? So for that, how it is, how we can implement, let us see. Now, if you are having the function like this, AB plus CD, this is in which form? You are having product term, sum together. This is what? SOP form. SOP form. Okay. So here question is by using NAND gates. Okay. So you are having the function SOP form. So you can apply 2 times complement. You will get the same functionality. For inner complement, you can use De Morgan's law. You will get first term complement and second term complement and keep external complement as it is. Okay. So that means with the help of one NAND gate, you will get this one. With the help of another NAND gate, you will get this one. After that, these 2 outputs, if you are passing through other NAND gate, you will get the overall expression. So that means whenever the question is regarding minimum number of NAND gates, okay, whenever they give any Boolean function, if they ask what is the minimum number of NAND gates required for implement that function, try to arrange the given function into SOP form. Try to arrange the given function into SOP so that you can easily implement that particular function with the help of NAND gates. Here we require 3 2-input NAND gates. We require 3 2-input NAND gates. Similarly, whenever they ask in the question, what is the minimum number of NOR gates required for implementing any Boolean function? Yes, very good, Hemant, very good. Suppose if you are having the function like this, I am considering random example only, A plus B into C plus D. Now this is what? Sum term, this is sum term, these 2 are product together, right? So this is the POS form. This is the POS form. So whenever you are having POS form, it is easier to implement with the help of NOR gates. Okay. So whatever the function you are having, you consider the same function and apply 2 times complement. You will get the same function. For inner complement, you can use De Morgan's law. First term complement plus second term complement and keep external complement as it is. So here also, if you observe, you require 3 NOR gates. 3 2-input NOR gates. So in this way, whenever the question is regarding NAND gate, try to arrange the function into SOP. Whenever the question is regarding NOR gates, try to arrange the given function to POS, like that. Okay. Either you can remember this representation, or regarding the logic gates also. Regarding logic gates. See, regarding NOT gate, there is no issue. How to implement with the help of NAND. Similarly, with the help of NOR. Regarding AND gate, by using NAND gate, there is no issue. Here also we are performing 2 times complement, but this function directly you are getting with the help of one NAND. After that, you are using NAND based inverter. Okay. Similarly, regarding OR gate, by using NOR gate, there is no issue. You will apply 2 times complement. First, initially you are getting this one. After that, you are getting this one. Okay. But if you want to implement AND gate by using NOR gate, if you want to implement AND gate by using NOR gate, that time what we have done? For inner complement, we have applied De Morgan's law. For inner complement, we have applied De Morgan's law, because Once if you are able to apply De Morgan's law, then you can implement this function with the help of NOR. Okay. Similarly, if you are having this function, if you want to implement by using NAND, for inner complement we have used De Morgan's law. Okay. So you can just remember the basic gates how we have implemented with the help of NAND or NOR, or you can just remember these two. Okay. It is very simple. Here you are having like two product terms, right? Sum together. It is something like here you are having OR gate. See, here you are having two variables in each term. Suppose if you are having only one variable, this is like OR gate only. This is only OR gate. Similarly, here also if you are having only one variable, this is like AND gate, right? So that's why if you are able to remember, okay, with the help of NAND gates, NOR gates, how we implemented basic gates, either with the help of this understanding or with the help of this understanding, you can answer any question regarding NAND gates and NOR gates regarding minimum number of gates in the GATE exam. Okay, whether it is regarding logic gate or whether it is regarding logic function. I hope it is clear for everyone. Is it clear for everyone? Yes. Right. So all of you take small break, 5 minutes you can take. So after the 5 minutes, we will continue from 4th chapter. So up to now I have discussed regarding first 3 chapters. So remaining 4 chapters we'll discuss after 5 minutes break. Okay. So if you want, you can take 7 minutes break. So currently time is 7:48. So we'll start the class at 7:55. Okay. Yes, we'll start from combination circuits, right? After 5 minutes, I will start. 5 to 7 minutes. At 7:55, I will start. Hello students, welcome back. All of you please respond. How many of you are eagerly waiting for the 4th chapter, combination circuits? All of you please respond. So far we have discussed first 3 chapters. Now we are going to start the 4th chapter. So in a combination circuit, okay, you're having one circuit, it is a digital circuit. Here outputs purely depend on the combination of present inputs. Outputs purely depend on the combination of present inputs. Hence we are calling this particular digital circuit as combinational circuit. Okay, yes, very good, Mayank. So can you give the examples of combination circuits where outputs depend only on the combination of present inputs? Outputs depend only on the combination of present inputs. So can you give the examples for combination circuits? Yes, very good. Binary adders, binary subtractors, magnitude comparator, yes, very good. Decoder, encoder, demux, mux. Yes, very good, Abhilash, Anand, Mayank. Yes, very good. All of you are correct. Magnitude comparator, decoders, encoders, demultiplexer and multiplexer. Okay, so these are the various combination circuits. Here in all these combination circuits, outputs depend only on the combination of present inputs. Okay. So among the binary adders, the first one is half adder. So for half adder, it will perform the addition of 2 single bits. And it will produce 2 outputs. So the first bit we will call it as sum bit and the other bit we will call it as carry bit. Okay. So here A and B are the 2 single bits. Okay. When you perform the addition, you will get, regarding sum, you will get A XOR B. Regarding carry, you will get A and B. See, if you observe, previously we have discussed logic gates. Each and every logic gate has got the respective name based on the logic function that is produced by it. Now if you see the here we are performing addition operation, but for performing addition operation we are using once again logic gates, right? So that is the beauty of logic gates. Individually each and every logic gate will produce respective logic function, but the set of logic gates we can use even for performing arithmetic operations. That means inside microprocessor you will be having ALU, arithmetic and logic unit. So for performing various logical operations you are having logic gates, and even for performing arithmetic operations we are using logic gates only, right? A XOR B, can you tell what are the minterm numbers? And similarly here, what is the minterm number? All of you please respond. Regarding sum, what are the minterm numbers? A XOR B. If you want this one, you can write as A bar B plus AB bar. So just by looking at these terms, you can tell the minterm numbers. A bar B. So that means A value is 0, B value is 1. Here A value is 1, B value is 0. 0, 1 is nothing but 1. 1 0 is nothing but 2, right? Yes. So that means here the min terms are 1 2, whereas here AB both are normal, so that means 1 1 is nothing but 3, so the min term 3. Yes, very good Anand. Yes, very good Abhilash, very good. So the min terms 1 2 are corresponding for sum, min term 3 is corresponding for carry. So this is the half adder. It will perform addition of 2 single bits and it will produce 2 outputs. One bit is sum, another bit is carry. Okay. Now next one is full adder. Next one is full adder. Full adder will perform addition of 3 single bits, among which A is 1 bit, B is 1 bit, and third input is the carry from the previous stage. And here also it will produce 2 outputs, and this bit as usual it is a sum bit, and this bit we will call it as carry out. Carry out. Okay. So what is a, so just tell me the min term numbers. Just tell me the min term numbers. You will get 4 min term numbers. And similarly for carry out, you will get 4 min terms. See, I will give the hint. Regarding sum, I know that all of you are familiar. Regarding the sum expression, you will get A XOR B XOR C, A XOR B XOR C, right? So just by looking at this expression, it is an exclusive OR operation among 3 inputs, right? So that means you have to focus whenever min term means output should be 1. So that means just observe the number of ones odd. Yes, very good, Mayank. Anand, yes, very good, very good. Okay, so whichever input combinations you are having odd number of ones, that time if you are getting 1, that is nothing but exclusive OR function, right? So 1 2 4 7, 1 2 4 7, right? So when you convert these numbers into binary, here you will get number of ones is 1, here you will get number of ones is 3. Number of ones is 1 or number of ones is 3, those two are the odd numbers. So for odd number of ones you are getting output as 1, that is nothing but XOR function, right? Similarly, regarding carry, see, when you are performing addition of 3 bits, the moment if any 2 bits are 1, you will get carry output as 1, or the moment if all the 3 inputs are 1, then also you will get carry output as 1, right? So just observe the combinations, in such a way that the moment if 2 inputs are 1 or all the 3 inputs are 1. Okay, so accordingly you will get 3 5 6 7, 3 5 6 7. So if you observe first 3 combinations 3 5 6, when you write in the corresponding binary, you will get 2 ones, whereas 7 if you write, you will get 3 ones. Okay, the moment if you are having 2 ones or all the 3 ones, then also you will get carry output as 1. Okay, right. So this expression regarding carry out, if you are using simplification by using K-map, you will get one expression like this: AB plus B into C in plus C in into A. By using K-map, if you do the simplification, you will get like this. Now you can observe here also, you are having 3 inputs A, B, C in. The moment if any of the 2 inputs are 1, 1 plus anything is 1, logical, or even if all the 3 terms are 1, then also you will get 1, right? So accordingly you are getting, the moment if 2 inputs are 1 or all the 3 inputs are 1, then you are getting 1. So accordingly you are getting this expression. Now if you are using, by using basic rules and laws of Boolean algebra, from the truth table if you write the min terms, after that if you sum together and do the simplification, from there you will get one more expression. Okay, one more expression you will get, that is A into B plus A XOR B into C. So both the functions are equivalent for the carry output. Okay, for the carry output you are getting 2 simplified functions. Okay, with the help of K-map you will get this one. With the help of basic rules and laws of Boolean algebra, you will get this equation. Both are equivalent. Okay, for your carry output. Based on the requirement, with the help of the set of logic gates of, here you require simply AND gates and then OR gate. Here you require combination of AND gates, XOR gate and then OR gate. So based on the requirement, you can use this equation or this equation. Okay, I hope it is clear for everyone. Right. Now if you observe here, for half adder we are using one XOR gate, one AND gate. Okay. Now similarly, if you observe here, we can get one XOR. After that, you can perform XOR operation with this one. Okay. So that means we require two XOR gates here. We require two XOR gates. Similarly, if you observe, here we require one AND gate. Okay. And similarly, here we require one AND gate. So this A XOR B is nothing but this one only. A XOR B is nothing but that one only. Now if you observe carefully, this sum equation and the final carry. Okay, what is your observation? Here one XOR gate, here we are using one XOR gate and then one AND gate. Okay, similarly one more XOR gate and one more AND gate. After that which logic gate we require? All of you please respond. One XOR gate, one AND gate for first stage, second XOR gate, second AND gate for second stage. Okay, after that we require third stage regarding carry output. Yes, we require one OR gate. Yes, very good. One OR gate. So that means if you observe this one and that one, XOR gate, AND gate, set is nothing but half adder. So like that you are having two half adders and one OR gate. Yes, very good Abhilash, very good. Okay. So that means for implementing a full adder, we require two half adders and one OR gate. For implementing a full adder, we require two half adders and one OR gate, right? So in a full adder equation, you are having the third input C in. You are having. Okay. So the moment if you are keeping C in is 0, all of you please substitute. If C in equal to 0, then tell me what is the sum equation you are getting here, what is the carry out equation you are getting here. Just observe, just substitute C in value 0, then full adder becomes what? If C in equal to 0, then full adder becomes I hope all of you are familiar. If C in equal to 0, then full adder becomes, yes, very good Anand. Full adder becomes half adder. See, in the half adder we are just performing addition of 2 bits, whereas here we are performing addition of 3 bits, whereas the third input is C in. The moment if you are keeping C in as 0, it is as good as what? Half adder only, because here number of inputs are 2, number of outputs are 2. Similarly here also, the moment if you are keeping C in as 0, you are having 2 inputs only and you are getting 2 outputs. So that means full adder becomes half adder. Even if you substitute here C in value 0 and do the simplification, the sum equation here and here it will match. Similarly carry equation will match. Okay, right. So that means if you want to implement 4-bit binary adder, then we require 3 full adders and 1 half adder, because here you are having 2 4-bit numbers. If you want to perform the addition, initially there is no carry input, so only half adder is sufficient, whereas for performing addition at the higher stages, you may require the carry input from the previous stage. So that means we require 3 full adders. With the help of 3 full adders and 1 half adder, we can implement 4-bit binary adder, right? We can perform 4-bit binary adder. But for uniformity, we can use 4 full adders. For uniformity, we can use 4 full adders. So actually at the last stage we require half adder, but we are using there also full adder. So that means carry input we will keep simply 0. Then full adder becomes half adder only, right? Right. So why we are using 4 full adders? The reason is very simple. Now in general, this 4-bit binary adder, you will cascade 4 full adders. Okay. For each full adder, you will give the respective A bits and B bits, and carry output of one stage you will give as carry input for other stage, right? So here since you are giving for each full adder AB inputs at the same time, so because of that, this particular binary adder we can call it as parallel binary adder. And one more observation point, the carry output of one stage we are giving as carry input for next stage. That particular phenomenon is called ripple phenomena, and that is happening because of the carry. So we can call this adder other name as ripple carry adder. Ripple carry adder. So whenever in the question ripple carry adder or binary adder, sorry, parallel binary adder, if they mention, both are referring same adder only. Okay, because inside each full adder, you are having XOR gates, whatever earlier we have written, the combination of with the help of half adders and then OR gate. Okay, regarding sum bit, it will perform parallelly. Similarly, regarding carry output, it will perform parallelly, right? So that's why here, since we are able to give all the A inputs, B inputs at the same time for all the full adders, we are calling it as the parallel binary adder, and the carry output of one stage we are giving as carry input for next stage. So because of that, we can call this adder as ripple carry adder. Okay. So in general, these 4-bit binary adders available in one IC form, chip form. Okay. So whenever you want to implement higher order adders, that time what we can do cascading, right? Cascading is nothing but output of one step we will give as input for other states, right? So if you want to implement 8-bit binary adder, that time how many 4-bit binary adders we require? If you want to implement 8-bit binary adder, how many 4-bit binary adders we require? See, you can consider 4-bit binary adder as single chip. Okay, so like that you can consider one more 4-bit binary adder. Yes, very good, Anant. Okay, so the carry output of first stage we will give as a carry input for next stage, right? So that's why here actually you require half adder, but instead of half adder, why I used full adder? Now I hope all of you got the clarity. Because if you are using only at the starting stage half adder, if you are cascading, that means if you are using the same entire block as one more block. Okay, if you want to give the carry output of this one as carry input, there is no possibility if you are using half adder at the first stage. Okay, but if you are using full adder, you can give the carry output of the last stage as the carry input for next stage, right? That's why we are using 4 full adders inside the 4-bit binary adder. So here for implementing 8-bit binary adder, we require 2 4-bit binary adders. Similarly, if you are using 4 4-bit binary adders, you will get 16-bit binary adder. So in this way, if you want to generate higher order binary adders, just by cascading 4-bit binary adders, you will get higher order adders, right? See, in general, if you are having a full adder, okay, if you are having a full adder, here inside each full adder, you are having this logic gate regarding sum and this set of logic gates for carry, right? So the moment if Cin is 0, each full adder, in order to produce the sum, it takes same amount of time. Similarly, in order to produce carry, it takes same amount of time. Okay. So for each full adder, in order to produce a sum, it takes Ts, and in order to produce the carry, it takes Tc. See, ideally speaking, the moment if you are given the inputs, you will get the output in no time, in 0 time. Okay, that is called ideal. But inside each and every logic gate, you will be having the transistors. In order to turn on or turn off or to change from one state to another state, definitely it will take some amount of time. That is called propagation delay, right? So for the starting state full adder, carry input is 0. So that time, the moment if you are giving AV inputs, in order to produce sum, it takes Ts delay. Similarly, in order to produce carry output, it takes Tc delay, right? So like that, if you are having n number of bits, okay, n number of bits, if you want to perform the addition by using full adders, okay. So in the question, if they ask to calculate worst case delay of n-bit binary adder, worst case delay of n-bit ripple carry adder, then here worst case means what? Any guess? here I am using 4 full adders. Okay, only at the starting stage there is no carry input. Okay, but at each and every stage, if the carry output is 1, then it is called worst case delay, right? Yes, very good, Anand. If carry output at each and every stage is 1, then we will call it is the worst case, because the last stage full adder has to wait for this carry, right? Then only what is the operation, final output you are getting, that will be valid. Okay, right. So here in the worst case, what we will do, that means at last stage, whatever the full adder you are having, regarding that particular full adder, we will calculate regarding the sum bit, how much time it is taking. Similarly, regarding carry, how much time it is taking. Among these two, whichever is the larger, that will be the worst case delay. That means after you are giving the inputs, in order to get the valid output, among these two, whichever is the larger, that much time you have to wait. Then only your answer, final answer will be correct. Before that also you may get some answer, but that may be correct or may not be correct, because each and every full adder, the moment if you are giving AB inputs, initially assume that Cin is 0. With the help of that, it will produce the sum bits and carry bits accordingly. But the moment if any stage carry is 1, carry output is 1, so once again it will consider that 1, accordingly it will update the respect to sum and carry bits. Okay, I hope it is clear for everyone. Now here in this case, instead of half adder, I am using full adder only. Okay, right. So for first stage carry, you are getting at TC. Second stage you are getting at 2 TC, because for each full adder, in order to produce carry, it requires TC only, right? But now observe, suppose if you are having fourth stage, so here this particular full adder has to wait for this carry. So this carry at what instant it is coming? TC plus TC plus TC, 3 TC, right? So that 3 TC plus TC, that is nothing but 4 TC, right? So for generalized case, I am writing it as, N into TC. I hope it is clear for everyone. See, first stage full adder, in order to produce the carry output as 1, worst case means carry output is 1. In each and every case, each and every stage carry output as 1, right? So this carry output you are getting 1 after TC. This one you are getting after 2 TC. This one 3 TC. Similarly, this one 4 TC, right? Yes. So in the same way here, N times TC. Correct. Yes, very good, Abhilash, very good. Similarly, if you observe regarding the sum at last stage, see this particular full adder, in order to produce the sum, it requires TS, but this full adder has to wait for this carry. This carry you are getting at what? If you are having n full adders, it is n minus 1 times, right? So that means here TS plus n minus 1 times TC. So it is very simple. You can easily remember these two formulas. Sorry, this is TC, sorry. Just one second. Yeah, first one is TC, second one is TS. Okay, right. So in this way, you have to calculate these two values, and among these two, whatever is the maximum, that will be the final answer. Maximum of TC comma TS. Okay, that will be the worst case delay. Okay, see, it is very simple. Suppose in the exam, in the question, if they mention that, whatever the values they are giving, based on that I am giving the classification. Suppose if TS is greater than TC, if sum delay is greater than carry delay of a particular full adder, if the carry input is 0, okay, then obviously when you calculate these two, okay, obviously TS only is greater when compared to TC. At last stage also, obviously the sum delay will be greater when compared to carry delay. Suppose if they mention both are same, then just verify what you are going to get. Just assume in the place of TS, TC. Here TC minus TC, both will get cancelled. You are getting NTC and TC, both are same, right? So that means if a full adder, when carry input is 0, if these two are same, obviously at the last stage also, the respective sum delay and carry delay both are same. Similarly, for last case, if TS is less than TC, then obviously at the last stage, TS only will be less when compared to TC, like that. Okay, so in this way, you no need to calculate both the values in all the cases. Okay, just by observing the relation between these two, accordingly you can use one of these two only. Okay, If this is greater, obviously you can use this one, or if this is greater, then you can use this one. If both are same, then you can use either of the equation. Since this equation is smaller or simpler, better you can use that one, right? So in this way you can calculate worst case delay of the ripple carry adder. Okay, so similarly you will be having half subtractor, full subtractor, 4-bit binary subtractor, etc. Okay, so later you can try. So it is very simple. So here when you are performing addition, you are getting sum. Similarly, when you are performing subtraction, you will get difference. Okay, and here you are getting carry, there you will get borrow, like that. Okay, so regarding sum equation, in the half subtractor, half adder, both are same, you will get same expression. Similarly, for full adder, sum equation and difference equation will be same. Only the difference, here I have considered C in, there you will get B in, borrow input. Okay, and here regarding carry, you are getting AB, there you will get borrow output. Okay, so there wherever you are having A, you can put A bar, that's all. Similarly here also, wherever A is there, you can put A bar, and wherever C in is there, you can consider B in. Okay, so that will be the regarding half subtractor and full subtractor, you will get the equations like that. Okay, next one is magnitude comparator. So as the name implies, here you are having comparator, that means you are performing comparison operation of what? Two numbers, and those two numbers magnitude wise it will check. So whenever you are comparing two numbers, okay, at the output you can say that whether A is greater than B, or A is less than B, or A equal to B. Okay, one of these three possibilities you will get. Okay, so just for easy understanding, I have labeled according to the relation, but if you want, you can label output as y2, y1, y0. Okay, whenever A is greater than B, that time only this output will be 1, other two outputs are 0. Okay, whenever this condition is satisfying, this output will be 1, other two outputs are 0. Similarly for last case, like that. Regarding magnitude comparator, just you have to identify the logic, that's all. Okay, in which case you are going to get output as 1, or in which case you are going to get output as 0, like that. Okay, so regarding magnitude comparator, sometimes they will give the minimized function. Okay, they will ask try to get the minimized function or equivalent function, etc., or regarding the number of combinations. Okay, for how many combination of inputs you will get A is greater than B or A is less than B, like that. Okay, so those are the simple questions. Based on the number of bits, you can write the corresponding combinations. Yeah, thank you, Amit. Thank you. Next one is decoder. So regarding decoder, the size will be n to 2 power n. N to 2 power n decoder. So here you will be having n inputs. So those n inputs are nothing but coded information. You will be having the information in the form of code. That one you are decoding with the help of 2 power n outputs. With the help of 2 power n outputs, you are decoding, right? So that's why we are calling that particular combination circuit as decoder, because it is performing decoding operation. Okay, so here we will use enable signal also. Whenever enable equal to 1, that time outputs of the decoder are nothing but minterms. Outputs of the decoder are nothing but minterms. Because here in the decoder, what will happen? You will be having n bits at the input side, right? So for each and every coded information at any time, only one among these 2 power n outputs will be 1, right? So that means the respective input combination is nothing but what? Minterms. That's why we are saying that enable 1 means what? Whenever you want to operate the circuit, that time you will enable it, right? Whenever you don't want to operate the circuit, you can disable it. Disable means enable value is 0, simple. Okay, so whenever enable is 1, based on the code information, at any time a particular output is 1. So that means whatever the decoder outputs you are getting, those are nothing but minterms. Those are nothing but minterms. Okay, so that means, say for example, if you want to implement one function like this, f of ab is equal to sigma m 1 comma 2. Suppose you are having one Boolean function like this. If you want to implement this function, okay, So here sigma m 1 2 you're having, that one you can write as m1 plus m2, m1 plus m2. So for implementing this function, can you identify the size of the decoder which we required? Can you identify the size of the decoder which we require? See, here how many variables you are having? 2 variables. So that means just substitute n value 2. So that means accordingly you will get 4. So 2 to 4 decoder, simple. 2 to 4 decoder, here D0, D1, D2, D3. Okay, when you are keeping enable as 1, okay, that time outputs are nothing but minterms. M0, M1, M2, M3. Okay, so when you are keeping enable as 1, outputs of the decoder are nothing but minterms. Now, in order to get M1 plus M2, which logic gate we require? Yes, obviously it is what? Logical OR operator, right? So you require only OR gate. So you have to pass minterms 1 and 2 through an OR gate. So you will get this function M1 plus M2. So that means whenever you want to, yes, Abhilash, very good. Yeah, Anant. See, M1 plus M2 is nothing but XOR gate. But here we want to implement that function by using decoder. Okay, in addition to decoder, we require OR gate, right? Simple. So whenever you're having the Boolean function, see, from the truth table you will get the output function either in the sigma m form or pi capital M, right? So whenever you're having sigma m form, with the help of decoder, when you're keeping enable as 1, you're getting the minterms. The respective minterms you can pass through the OR gate. Okay, so this is one more application of the decoder. In the real time, the decoder, according to the name, one functionality you're having, that is performing the decoding operation. This is one more application. Since you are getting the minterms, okay, you can call decoder as minterms generator, because decoder is producing minterms. So we can call decoder as minterms generator because it is producing minterms, right? Minterms generator. Similarly, we can use decoder in the memories also. Okay, so regarding that, you will learn in the semiconductor memories or in the CO subject also, those who are from computer science or EC. Okay, earlier microprocessor is there, so even in the microprocessor also you will learn regarding the memory, size of the memory. There also we will use decoder. So in this way, you're having number of applications regarding decoder. Next one is encoder. So it is exactly opposite to that of decoder. So encoder, the number of inputs are 2 power n and you will get number of outputs are n. So you are having the whatever the 2 power n input lines you are having, that one you are representing with the help of n bits. That means you are performing coding operation or encoding, we will call. Encoding or coding, both are same. Okay, so that means just if you observe, regarding the decoder, at any time only one output is 1. So in the same way, for a normal encoder, at any time only one input should be high. At any time only one input will be 1. So that accordingly you will get the respective coded information. Okay, so this is the mandatory condition for the normal encoder. Okay, but suppose if more than one input is 1 because of any reason, suppose if you are giving externally inputs from your side, you will make sure that among these 2 power n inputs, at any time you will give only a particular input is 1. But if you are getting these inputs from the output of some other circuit, there you don't have any control. Okay, so sometimes you may get more than one input also 1. Okay, if you are getting like that, then you may get the false code or wrong code. Okay, so to avoid that one, we will use priority encoder. So with the help of priority encoder, what we will do here, whatever the 2 power n inputs you are having, for each input we will assign the priority. Okay, among those inputs which is having highest priority, which is having lowest priority, what is the priority order, etc. we will assign, so that even though more than one input is 1 because of any reason, still you will get the code corresponding to the input which is having high priority. Okay, so whatever the drawback is there in the normal encoder, we can easily overcome if you are able to assign priority to each input. Okay, then it is called priority encoder. And then with the help of decoder and encoder, suppose if you are observed here, you are having n bits here, 2 power n outputs. Okay, and similarly if you are using normal encoder only, here number of inputs are 2 power n, number of outputs are n. So that means if you are using the combination of decoder and encoder, you can perform various code conversions. You can perform various code conversions, like suppose if you want to convert binary to gray, or gray to binary, or binary to BCD, or BCD to binary, or BCD to XS3, or XS3 to binary. So in any one form of the code to another form of code, if you want to convert by using both decoder and encoder, combination of decoder and encoder, we can use for performing various code conversions. We can perform various code conversions. So this is the real-time application by the combination of decoder and encoder. Whatever the course you have studied in your first chapter, if you want to convert one form of code to another form of code, or even if you want to convert binary information into 2's complement, or 1's complement, or 1's complement to 2's complement, any form, if you want to convert with the help of decoder and encoder, you can implement any code conversion. Any code conversion you can perform. Next one is demux. So in the multiplexer, here we are using demux, that means reverse operation of mux, right? So here the size of the demux will be 1 by 2 power n. Here you will be having single input line, and this input line we will connect to one among these 2 power n outputs. So this input will be connected to among these which output we have to connect, that is based on n selection lines. So with the help of selection lines, you can connect this input to one among these 2 power n outputs. So that means it is just like acting like a switch, right? So you can call demux is acting like a switch. In one sense we can say, because you are having one input, that input you are connecting to one among 2 power n outputs. Okay, and if you observe here one more important observation, here number of inputs are 1. So whenever number of inputs are 1, we will call it is serial input, because you are giving bit by bit input. Okay, whereas here 2 power n outputs are there. So multiple outputs are there. So that means we will call it as parallel. So because of that, we can call demux acting like serial to parallel converter. Yes or no? So this is one more application. With the help of demux, we can do the conversion of serial to parallel. So with the help of selection lines, one bit you can consider, and you can give you can connect that input to one of the 2 power n outputs one by one. After that, when you are getting all the 2 power n bits, okay, that time you can connect the entire 2 power n outputs at the same time to other parallel device which can accept the input parallelly at the same time. Okay, so in that way, whenever you want to interface one serial device to parallel device, that time you can use demux. Now if you observe regarding demux, I have told one application it is acting like a switch, and one more application we have told that serial to parallel converter, right? Now application wise decoder and demux both are different. But hardware point of view or circuit point of view, there is a similarity. Whether hardware circuit point of view, whether both are same or not, all of you please respond. Regarding decoder and demux, hardware point of view, whether both are same or different. Application wise both are different. I am asking with respect to when you draw the circuit diagram. Say for easy understanding, if you are having 1 by 4 demux, and if you are having 2 to 4 decoder, just observe these two. Yes, hardware point of view, circuit point of view, both are same one. So just observe, here you are having number of outputs 4, here also number of outputs are 4. Number of outputs are 4. So that means we will use 4 AND gates. We will use 4 AND gates. Similarly, here also we will use same number, 4 AND gates only. 4 AND gates only. Right. Here you are having one input. Okay. But here we will use one input, that is enable. Okay. So this input you can label as I. So this input I and this input enable. You can correlate. Okay. And then here we require 2 selection lines, S1, S0. 2 selection lines we require. Here 2 inputs, AB. Okay. So for each AND gate, you require 3 inputs. For each AND gate you require 3 inputs. Okay. So that means hardware point of view both are same. Okay. Suppose if you are having demux, if your requirement is decoder, you can use same demux as decoder. Similarly, if you are having decoder, if your application is demux, same decoder only you can use as demux. What modification you have to do? It is very simple. Regarding outputs, it is same. Okay. So say for example, if you are having a decoder, if you want to use as demux, for demux you request serial input. That serial input you will connect to the enable. Okay. And here you require selection lines. That selection lines you will connect to this one. Similarly, if you are having decoder, if you want to use as demux, okay, then accordingly you can connect the connections accordingly. Okay, reverse like that. That's all. Application wise both are different, but hardware circuit wise both are same. That's why if you are having decoder, we can use as demux, and if you are having demux, we can use as decoder, vice versa. Okay, I hope it is clear for everyone regarding demux. Okay, now let us proceed to the next one, that is multiplexer. In short, we will call it as mux. See, here the functionality is just opposite to that of demux. Okay, so here you will be having 2 power n inputs and the number of outputs are 1. Okay, so here which input has to be connected to the output, that is based on n selection lines. Okay, right. So that means we can say mux is also acting like a switch, just like demux. In the demux case, you are having single input line. That input line we are connecting one among 2 power n outputs based on this n selection lines. But here in this case, you are having 2 power n inputs. So at any time, only a particular input will be connected to the output, right? So that is based on n selection lines. And here if you observe, the number of inputs are many, 2 power n. So you can say multiple inputs are parallel inputs, but here number of outputs are 1, so you can say it is a serial output. So that means with the help of this understanding, we can tell that mux is we can use mux as parallel to serial converter. So whenever you want to interface one parallel device with the serial device, that time you can use mux as the interfacing device. Okay, with the help of mux, we can interface one parallel device to the serial device like that. So if you are having 2 by 1 mux, for 2 by 1 mux, you are having 2 input lines and 1 selection line. Okay, for 2 by 1 mux, the output equation you will get, if the selection line is 0, I0 will be connected. If the selection line is 1, I1 will be connected. So S bar I0 plus S into I1. Similarly, for 4 by 1 mux, you require 2 selection lines. So the output equation is based on the selection lines. Okay. So if the selection lines, both the values are zeros, 0, 0, then that time I0 will be connected. For 0, 1 combination, I1 will be connected. For 1, 0 combination, I2 will be connected, and for 1, 1 combination, I3 will be connected. Okay. So in this way, you can use whenever you are having 2 by 1 mux or 4 by 1 mux, accordingly 8 by 1 mux. Okay. Just based on the selection lines, at any time a particular input will be connected to the output. Okay, right. You can use these standard equations whenever you want to find out the overall output of the mux. Okay. After that, if you want, you can convert the output into the sigma m form or pi capital M based on the given choices. say for example, if we want to implement AND gate, if we want to implement a 2-input AND gate by using MUX, how we can implement, let us see. So first write the truth table of AND gate. So this is the truth table of AND gate, y equal to a and b, y equal to a and b. So whenever both the inputs are 1, then only you will get output as 1. The moment if any one of the input is equal 0, you will get output as 0, right? So now this is the truth table of AND gate. This is the truth table of AND gate. Now we want to implement this AND gate with the help of see. First let us implement with the help of 4-by-1 mux. If you are using 4-by-1 mux, for 4-by-1 mux you will be having 4 inputs. So you can assume the inputs as I0, I1, I2, I3, and you require 2 selection lines S1, S0, S1, S0, and the final output you will get Y here. Okay, right. Now here you are having 2 variables AB, right? So you can choose these 2 variables as selection lines. You can choose AB as the selection lines. Now with respect to mux functionality, when you are having 0, 0, I0 will be connected to the output. When you are having 0, 0, I0 will be connected to the output. But for 0, 0 combination, you are already having output as 0. So that means I0 is nothing but 0. I0 is nothing but 0. For 0, 1 combination, I1 will be connected. But for 0, 1 combination, according to the truth table, you already know the output value 0. So that means for 0, 1 combination, I1 will be connected. Since the output is 0, I1 will be 0. Similarly, for 1, 0 case, I2 will be connected. So here 0. Similarly, for 1, 1 case, I3 will be connected. But here you are having 1. So in this way, it is very simple. It is very simple. Whatever may be the logic function or logic gate, if you want to implement, whatever may be the number of inputs, okay, you can implement any Boolean function or any logic gate with the help of single mux. With the help of single mux, provided the number of input variables and number of selection lines both are same. Number of input variables and number of selection lines, if both are same, you no need to do any simplification. Just you will see with respect to selection lines, whatever the combinations you are having, whether you are having in the same combination or not. If you are having in the same combination, whatever the output column you are having, just copy paste. That's all. No need of any simplification at all. Okay. So with this understanding, can we say that mux is a universal element or not? All of you please respond. How many of you are agreeing mux is a universal element? Yes or no? See, with the help of NAND gates and NOR gates, with the help of NAND gates alone and similarly with the help of NOR gates alone, we can implement any Boolean function. In the previous chapter we have discussed. Similarly, now we are telling that with the help of single mux, you can implement any Boolean function. You can implement any Boolean function provided the number of input variables and number of selection lines both are same. With the help of single mux, you can implement, right? Yes, very good, Anant, Mayank, Abhilash. Yes, very good. That's why we can call mux is a universal element. So there is no need of doing any simplification at all. So whenever you are having the truth table, you will know how many inputs are you are having and how many outputs are you are having. So for each output you require 1 mux. That's all. How many output variables you are having? For each output variable you require 1 mux, and choose the selection lines is same as the number of variables. Okay, right. In this way you can implement all the logic gates. Whatever the output column you are having, you can copy paste. Now let us see all the logic gates with the help of 2 input mux. That means by using 2-by-1 mux. Okay. Now let us implement all the logic gates by using 2-by-1 muxes. Implementation of logic gates using 2-by-1 muxes. Okay, First, let us consider NOT gate. See, first write the standard equation regarding 2 by 1 mux. Standard equation regarding 2 by 1 mux, y equal to s bar I naught plus s into I1. Just observe this equation and accordingly we can write, that's all. For NOT gate, the output is nothing but a bar. So a bar means it is matching to the first term, right? So just you can rearrange this one like this. A bar into I naught is nothing but 1 plus a into I1 is nothing but 0. So consider I naught as 1, I1 as 0. Then the 2 by 1 mux will act as NOT gate, that's all. Next one is AND gate. So output is A and B. So that means it is matching to the second term. So that means in this case A bar into 0 plus A into 1, A into B. Yes, very good Abhilash. Yes. Similarly, next one is OR gate. OR gate output is y equal to a plus b. Now, if you want to implement this one, if you want to compare with that one, it seems to be difficult. But if you are able to recall regarding distributive law, before the break, in the second chapter I have discussed distributive law first. After that I have asked one equation. What is that equation? A plus a bar b. A plus a bar b if you are having, by using distributive law what you will get? A plus a bar is 1, so you will get a plus b. So when I asked this question, all of you told that a plus a bar b is nothing but a plus b. Now we are having a plus b, we can write like this, right? Now just I am arranging like this. A bar into b plus a into 1. Now it is matching, right? Similarly, next one is NAND gate. Okay, regarding NAND NOR, we'll write little later. Okay, for easy understanding, let us proceed with XOR gate. So XOR gate, y equal to a exclusive or b, which is nothing but a bar b plus ab bar. It is very simple. It is directly matching a bar into b plus a into b bar, right? Yeah, thank you Ankit, thanks a lot. Next one, XNOR gate. So y equal to a exclusion or b, that is nothing but a bar b bar plus ab. Now it is matching, right? Similarly, let us write other two logic gates, that is NAND gate and then NOR gate. So regarding NAND gate, y equal to a into b whole bar. Okay, so by using De Morgan's law, this one you can write as ab bar is nothing but a bar plus b bar. Now if you observe this equation, it maybe seems to be difficult, but whatever the logic here we have done, apply the same logic. Okay, here a plus b we have written as a plus a bar into b. In the same way, this one we can write as a bar I am keeping as it is. Now I am considering a. See, a bar plus a is 1, you will get a bar plus b bar, same term you are getting, right? Correct. Yes, very good Abhilash, very good. Now this one you can compare with that equation, a bar into 1 plus a into b bar. Similarly, NOR gate, y equal to a plus b whole bar, that is nothing but a bar into b bar. So here there is no issue, directly you are getting a bar into b bar. Okay, so that means a into 0 you can write, that's all. So here if you observe, for a NOT gate in general you will be having a as the input, output you will get a bar. Okay, here I naught is 1, I1 is 0, there is no issue. Regarding AND gate, you will be having inputs are a, b, normal form. Here 0 is I naught, I1 is b, there is no issue. Okay, similarly for OR gate, I naught is b, I1 is 1, there is no issue. Now clearly observe, here for XOR gate, in general you are having the inputs are AB. Okay, here normal input only, but here complement input B bar. Okay, here also you are having complemented B. Similarly, here also you are having complemented B. Similarly, here also you are having complement B. In general, whenever you are considering any logic gate, you will be having the inputs in the normal form, right? So you don't have the complement version. See here, if you observe equation 4, 5, 6, 7, you are getting one of the input as B bar. One of the input as B bar. See in the exam, if they ask what is the minimum number of 2 band muxes required, okay, based on the context, the answer will vary. Based on the context, the answer will vary. Say for example, in the question, if they say that if the inputs are available in both normal and complemented forms, if both normal and complemented forms, if both normal and complemented form, if the inputs are available, if the inputs are available in both normal and complemented forms, then for implementing XOR gate, XNOR gate, NAND gate, NOR gate, the minimum number of 2 band muxes required is how much? All of you please respond. If both normal inputs and complement inputs are available, for implementing XOR gate, XNOR gate, NAND gate, NOR gate, what is the answer? Only one. Yes, very good. Only one. For each case, we require only one. For each case, we require only one. Okay, if the inputs are available in both normal and complement forms. Okay, and sometimes if they will tell that the normal inputs are available, but in addition to that, NOT gate is also available. Okay, so then also the answer is 1, because here if you observe all these equations, you are getting B bar only one input complement version. So that means the same answer will applicable even if they say that inputs are available in the normal form and NOT gate is available. Then also the same answer. The number of 2 band muxes required is only one. But if they don't say anything about complement inputs, if they don't say anything about NOT gate is available, that means by default the normal inputs are available. Now can you tell what is the answer? If only the normal inputs are available, then for each case, what is the answer you are going to get? Yeah, thank you, Gopal. Yes, very good, Anand, Abhilash. Yes, very good. So we require 2. We require 2 band muxes, because whenever they say that only the normal inputs are available, that means whenever you are getting complement version, that time you can use this NOT gate. Here if the selection is A, you are getting A bar. If you are choosing selection as B, that time you will get B bar, right? So in this way, it is very simple. See, the concepts of digital seems to be simple, but you should be smart while you are answering in the real gate exam, because the paper setter are so smart that based on the context, your answer will vary. Okay, if you haven't read the question carefully, then you might be strong at the concept, but you may choose wrong answer, right? So this is very important. In the entire digital circuit subject, whichever question you are attempting, please read the question carefully. Whatever the main keyword is there, if you are able to catch, then definitely whatever the answer you are choosing, definitely it will be correct. But the moment if you are forgetting or if you are not caring about the main keyword, damn sure your answer, there is the most chances are there in order to get the wrong answer, right? So try to avoid that kind of silly mistakes, okay, because later after the exam over, you may feel regret, right? Even though you are good at concept, even though you know complete operation, but if you are wrongly attempting the dead easy question, then you will feel regret, right? So try to avoid such kind of situations, okay? So even though question is simpler, but please pay attention, try to read the question with careful. Okay, so it is very important for each and every subject. It is most important for digital subject. Okay, right. Yeah, native marking is there only for MCQ, whereas for MSQ and NIT there is no native marking. So it is very important whenever you are attempting any question in the GATE exam. If your answer is 100%, if you are confident about your answer 100%, then only you attempt. Okay, otherwise don't take risk regarding with the help of regarding the native marking. Okay, right. So with this we have completed the combination circuits. Now let us proceed to the next chapter, that is sequential circuits. So sequential circuit is also a digital circuit. Okay, what is the difference between combination and sequential? Any guess? What is the difference between combination and sequential? Regarding combination, we already given the definition earlier. So what is the basic difference between combinational and sequential? Yes, very good, Anand, very good. See, in general, in the combination circuit, outputs depend only what are the present inputs you are giving, right? But here in this case, in the sequence circuit, output not only depend on the present inputs, outputs depend not only on the present inputs, but also on the previous outputs or past outputs. That means, see, for any circuit, if you are giving present inputs, there is no issue. But if you want to give the previous output as one of the input, obviously you have to store the previous value somewhere. So for that you require memory, right? So that means combinational circuit along with memory is nothing but sequential circuit. Combinational circuit along with memory is known as sequential circuit. Yes, as you already told, yes, definitely we are using feedback, because if you want to give the previous output as one of the input, obviously you are using the feedback, correct? Yes, very good, Mayank, Anand. Yes. So regarding sequence circuits, can you guess what are the examples we are having? Hi, Suraj. Yes, we are having flip-flops, counters. Yes, very good. Registers. Yes, we are having latches, flip-flops, registers, and counters. So these are the various sequential circuits, right? Yes. So here if you observe, regarding latches and flip-flops, we will use latches and flip-flops for storing one bit of information. Okay, the only difference between latch and flip-flop, latches we will operate only at the levels. Okay, latches we will operate only at the levels. Say for example, this is the enable signal. Okay, so here if you observe, this is 0, this is 1. So that means you are having two levels. Either you can operate when enable is 0, or you can operate the circuit when enable is 1. That means we are operating only at the levels, right? Right. Correct. So whereas flip-flops, we will operate. Suppose if you are having clock signal, okay, here 0 to 1 transition is happening, and the other one I am considering like 1 to 0. Okay, so here if you observe, flip-flops we will operate only at the edges, right? Suppose if you observe here, you are having this is 0, this is 1. Okay, so from 0 to 1 transition is happening. There is one edge is there. So if you observe this particular edge, this is called raising edge or positive edge. Raising edge or positive edge. Raising edge or positive edge. Similarly, if you observe this clock signal, okay, here the clock signal transitioning from 1 to 0, or you can say high to low. So because of this one we can call it as falling edge or negative edge. Falling edge or negative edge. Falling edge or negative edge. So that means latches we will operate only at the levels, either when enable equal to 1 or enable equal to 0. Okay. Similarly, flip-flops we will operate only at the edges, either clock signal transitioning from 0 to 1 or clock signal transitioning from 1 to 0. Okay. So regarding latches and flip-flops, the equations will remain same. Okay. But only the difference in latches we will use the enable signal. Okay. Whereas in flip-flops we will use clock signal, because we are operating only at the edges. So for that we have to give the periodic square waveform. Okay. So we are focusing only at the edges. Okay. And then here present state I will represent as Qn and next state as Qn plus 1. Qn is nothing but present state and Qn plus 1 is nothing but next state. Okay. Whereas in the flip-flops we can use present state is nothing but Q of t. Present state is nothing but Q of t and the next state as Q of t plus 1. This is the representation we will follow, but whatever the equations you are getting in latches, the same equations will applicable for flip-flops. Okay. But only the difference where we are operating, whether we are operating at the level or whether we are operating at the edge. That's all. Okay. So if you want to solve any question in the GATE exam regarding sequence circuit, if you are able to remember the 4 characteristic equations of latches or flip-flops, that is more than sufficient to solve any question regarding sequence circuits. Okay. But you have to be very focused where that kind of operation is going to take place. That's all. That's all. Okay. Just if you are able to remember the 4 characteristic equations, that is more than sufficient. So all of you note down these characteristic equations. So for the timing I am writing with respect to flip-flops. The same thing will applicable with respect to latches. Only thing notation wise different. That's all. Okay. Right. So regarding SR flip-flop, the characteristic equation is Q of t plus 1 is equal to S plus R bar into Q. S plus R bar into Q. Next, D flip-flop, characteristic equation Q of t plus 1 is equal to D. Next, JK flip-flop, characteristic equation Q of t plus 1 is equal to J into Q bar plus K bar into Q. J into Q bar plus K bar into Q. Next, the last one, T flip-flop, Q of t plus 1 is equal to T exclusive or Q. T exclusive or Q. If you are able to remember these 4 characteristic equations, that is more than sufficient to solve any gate question related to sequence circuit. Because whatever the resistor you are considering or counter you are considering, inside that resistor or counter you are having flip-flops only. Okay. Right. All the flip-flops are edge sensitive. Okay. So whatever the equations here we have discussed, the next state transition will be updated based on the respective edge, according to the respective edge, whether it is positive edge or negative edge. Okay, that time only your output will be affected. That's all. Okay. So regarding D flip-flop, it is very simple. Just before the edge, whatever the D input you are having, the same input you will get just immediately after the edge. Okay. So regarding T flip-flop also it is same, simpler, T exclusive or Q. That's all. Okay. So regarding JK flip-flop, J Q bar plus K bar Q, whereas here SR flip-flop, S plus R bar Q. Okay. So by practice you can easily remember these 2 equations. Okay. Right. Now, if S input, see, regarding flip-flops, sometimes they will give the circuit diagram with the help of one flip-flop and with the help of some logic gates and with the help of some feedback connections. They will make the connections and they will ask what is the overall circuit, or they will ask what is the next state you are going to get, etc. Right? Right. So for solving any of these questions, it is very simple. Whatever the flip-flop given, first you can write the characteristic equation of that given flip-flop. And for that flip-flop, whatever the number of inputs you are having, according to the circuit, just find out those inputs and substitute in the respective flip-flop characteristic equation and do the simplification. That's all. Okay, right. So I will ask simple questions. If S and R inputs are complement, to each other, then SR flip-flop will become what? If SR inputs are complement to each other, then SR flip-flop will become which flip-flop? Yes, very good, Hemant. Yes. See, it is very simple. See, first, what you have to do, here I have mentioned that SR inputs are complement to each other, then SR flip-flop will become which flip-flop? Okay. So, first you have to write the characteristic equation of SR flip-flop, right? So, SR flip-flop characteristic equation is S plus R bar Q, S plus R bar Q. But here in the question I have mentioned that SR inputs are complement to each other. Say for example, if you are considering that S equal to X, then R will be X bar, R will be X bar. If R is X bar, then R bar will be X, R bar will be X. So just substitute here. So S is nothing but X, R bar is nothing but, that is also X, and then Q. So you can take X as common, then 1 plus Q you are getting. Either Q value is 0 or 1, irrespective of that, 1 plus anything is 1, because it is a logical OR, right? So you are getting simply X. Now if you observe these 4 equations, it is matching to this equation. So that means if X equal to D, then it is a D flip-flop. If X equal to D, then it is a D flip-flop. Then it is a D flip-flop. Okay. Similarly, if J and K inputs are complement, if J and K inputs are complement, then JK flip-flop will become which flip-flop? Any guess? If J and K inputs are complement to each other, then JK flip-flop will become which flip-flop? All of you try. Yeah, most of you are giving T flip-flop. No, generally students will do mistake here. Yeah, it is the D flip-flop. Very good. See, the moment if SR inputs are complement or JK inputs are complement, then SR flip-flop will become D, and similarly JK flip-flop also will become D flip-flop. Okay, right. See, even if you observe the truth table regarding SR and JK, first 3 combinations, for 0 0 no change, for 0 1 0, for 1 0 1. First 3 combinations regarding SR flip-flop truth table and JK flip-flop truth table, both are same. Both are same. That means when you observe the second row or third row, so for SR case, you will be having 0 1 case or 1 0 case. Your next state is what? Your next state is here 0, here 1. Okay, this is about SR. Similarly for JK, even if you are considering JK, you will get the same truth table. Yes or no? For SR flip-flop and JK flip-flop, okay, first 3 rows are same. First 3 rows are same. Now the question is what? SR inputs are complement. SR inputs complement means you are having a combination like this. If S is 0, R is 1, or S is 1, R is 0. Okay, then what you are getting? Whatever the S input you are having, you are getting the same thing. Whatever the S input you are having, you are getting the same thing, right? Right. Similarly, regarding JK flip-flop truth table also, first 3 rows are same. So since the question is regarding complement each other, I am considering second row and third row only, right? So here also, whatever the J input you are having, it is matching to the output, right? So that means here, yes, we have assumed X. So that X is nothing but if you are assuming D, it is a D flip-flop. In the same way, it is very simple. Here, whatever the J input you are having, that one you are getting. So it is very simple. Whenever SR inputs are complement or JK inputs are complement, Okay, then SR flip-flop and JK flip-flop will become simply D flip-flop. That is nothing but whatever the S input you are having, that you are getting, or whatever the J input you are having, that you are getting. That's all. That's all. And as you all know that whenever J and K are equal, that time it is a T flip-flop. Simple. Okay, if J and K are equal to T, it is T Q bar plus T bar Q, which is nothing but T XR Q, right? If J and K are equal, then it is a T flip-flop. Generally, students will do the mistake here. If J and K are complement each other, they will mention T flip-flop, but that is not correct. It will become T if J and K are same. Okay, if J and K are complement or S and R are complement, your SR flip-flop and JK flip-flop will become D flip-flop. That's all. So this is about flip-flops. Okay, now let us see regarding registers. So register is nothing but the group of D flip-flops. Okay, if you are having single D flip-flop, with the help of one D flip-flop, we can store one bit of information. If we want to store multiple bits of information, then we will cascade multiple D flip-flops. That's all. Okay, generally we will be having the representation like this. So we will cascade multiple D flip-flops. That's all. Okay, so the group of D flip-flops is nothing but register. If this register is having the capability of shifting the bits either towards right hand side or towards left hand side, then we will call that particular register as shift register. If the register is having the capability of shifting the bits either towards right hand side or towards left hand side. Okay, so accordingly we can classify the shift registers into two types. One is left shift register. Another one is right shift register. Okay, so this is based on the direction we are classifying the shift registers into two types. Similarly, whenever you are having, say for example, for the timing I am considering right shift register. For the timing I am considering 4 bits, right? So here we will perform shifting operation towards right hand side. Okay, and we will give the input like this. Okay, right. So here right shift operation is taking place. Now for this shift register, okay, so that means you are having, suppose it is the 4-bit case, so that means we are having 4 D flip-flops. For the entire configuration, if you are giving only one input and if you are taking only one output, okay, at a time you can give only bit by bit, and at a time you can access only bit by bit. So that means this particular shift register we can call it as serial in, serial out shift register. For the timing I have considered right shift. Similarly, if you want, you can consider left shift. There is no issue. Similarly, if you are giving only bit by bit serially, but if you are able to access parallelly from each flip-flop, if you are able to access output at the same time, then it is a serial input we are giving, but parallelly we are accessing the output, right? Yes, it is a serial in parallel shift register. Similarly, if you are able to give the inputs parallelly for each flip-flop at the same time, and if you want to access only bit by bit only one bit at a time, right? So that means parallelly you are giving the input, but serially you are taking the output. That is called parallel in serial out shift register. Similarly, the last case, you can give parallelly the inputs at the same time for each flip-flop at the same time. Just you have to apply one clock edge. The moment if you are giving one clock edge of the flip-flop, okay, for all the flip-flops you are having the same clock signal. The moment if you are given the input, after applying one clock edge, you will get the corresponding output. So that is called parallel in, parallel out shift register. Okay, so just by observing these 4 shift registers, can you guess that among these 4 shift registers, which one is the faster, which one is the slower? Which one is the fastest, which one is the slowest? Yes, very good, Hemant, very good. Yes, obviously parallel in, parallel out shift register is the fastest shift register. Because For all the flip-flops, you are giving the input at the same time. You are giving for all the flip-flops the clock edge at the same time. The moment if you are given the clock edge, you are getting whatever the input you are having, you are getting immediately, right? Yes, very good, Anant, very good, Hemant. Obviously, just by observing here, this one is the slowest. Serial in, serial out shift register is the slowest shift register. So that means whenever you are having the big circuit or system, right? All the circuits may not respond at the fast. All the circuits may not respond at slow. Okay, some devices can respond at fast, some devices can respond at slow. So whenever you want to interface one fastest device with the slowest device, definitely what you have to do, fastest device is producing the output at fast rate, but slowest device can access the data very slowly, right? So whenever you want to interface these two circuits or devices, obviously there is some interfacing device, right? So with the help of serial in, serial out, you can provide the delay based on the requirement. Similarly, parallel in, parallel out you can use whenever you want to do the conversion at fast rate, like that. Okay, so serial in, serial out shift register we will use as a delay liner. Okay, right. And if you observe these two, here input is serial, output is parallel. Here input is parallel, output is serial. So that means shift registers we can use for serial to parallel conversion, and parallel to serial conversion. Even we have discussed in the combination circuit also, demux we are using as serial to parallel and mux we are using as parallel to serial. Now with the help of shift registers, also we can perform serial to parallel and parallel to serial, but only the difference in the combination circuit, with the help of selectionize we can operate the circuit, whereas here in the shift registers with the help of clock signal we can operate the circuit. That is the only difference. I hope all of you got the clarity regarding the operation and application wise regarding the shift registers. Now for each and every shift register, if you are giving the input either serially bit by bit or parallelly at the same time, externally from your side if you are giving, then we will call, according to this particular sequence circuit is nothing but shift register. But if you are with the help of some feedback mechanism or with the help of some logic gates, whatever may be, if you are giving some part of the output, if you are giving as the input, okay, so that means what, this particular shift register will continue the operation continuously, right? So that means instead of giving serial input externally from your side, if you are giving part of the output as the input, then this particular shift register we can use as yeah, Hemant, among those two, serial in, parallel out. Based on the number of bits it may vary case to case, but the moment if you are getting parallel output, that means you may get input bit by bit serially, but parallelly you can access the output, right? Yeah. Right. So now what I am asking you, that if you are not giving input externally from your side, okay, so through some mechanism if you are giving the input, now this shift register we can use as counter, right? So the next topic is counter. A shift register is said to be a counter if it repeats particular sequence of states. Okay, so just now we have mentioned that inside the shift register we are having D flip-flops. Okay, so with the help of D flip-flops we are having two types of counters. One is ring counter, another one is Johnson counter. Okay, so for n bit case, if you are considering for n bit case, okay, in the ring counter we will use n D flip-flops. In the ring counter we will use n D flip-flops. Similarly in the Johnson counter also we will use same number of D flip-flops. Yeah, thank you Hemant, thank you. Right, in the ring counter and Johnson counter, see the number of bits, whatever the number of bits you are having, that many D flip-flops we will use, right? Now with the help of ring counter you will get only n states. Suppose if you are using 3-bit ring counter, see you are having serial in, parallel shift register, here the last stage output we will connect as serial input. Okay, the last stage output will connect as serial input. That is forming what? Closed structure or ring structure, right? Whereas in Johnson counter, see, for each and every flip-flop you are having normal output and complement output. The last stage complement output we will give as serial input. That means instead of providing the normal output, we are providing the complement output. That means there is a twist is there, right? Suppose if you are getting normal output as 0, but here you are getting 1, 0 bar is 1 or 1 bar is 0, right? That much twist is there. So accordingly, the other name for Johnson counter is nothing but twisted ring counter. Twisted ring counter. Okay, right. So, yes, Mayank, for the time being, I am considering right shift operation only. Serial and parallel shift register you can consider, and the last stage normal output you can give as the clock signal. For each flip-flop, clock signal is same. Correct. Right. So here you are getting n states. So because of that, the mod value for this counter is mod n counter. Mod n counter. Okay. Similarly, by using n-bit Johnson counter, you will get the number of states as double when compared to the number of bits or number of flip-flops. You will get 2n states. You will get 2n states. Okay. So that means here the mod value will be mod 2n counter. Mod 2n counter. Mod 2n counter. So that means here number of unused states are how many? Number of unused states. See, whenever you are having n bits, total number of combinations you will get 2 power n. Total number of combinations you will get 2 power n. 2 power n, but out of which we are using only n states. So subtract this number from total, that is nothing but unused states, number of unused states. Yes, very good, Hemant, very good. Yes. Similarly here you are getting 2n states, so that means the number of unused states are 2 power n minus 2n. See, with the help of shift registers, we are unable to get all the states because here only shifting operation is taking place. Now, if you are having n bits, if you want to get all the 2 power n combinations, now can you guess which flip-flops we will use? Instead of D flip-flops, which flip-flops we will use? Can you guess? If you want to get all the 2 power n states, we will use T flip-flops. If you are using T flip-flops, then you will get n-bit binary counter. N-bit binary counter. Okay. So here we will use NT flip-flops. We will use NT flip-flops, right? Very good. Here T value we will keep 1 so that output will become complement of the previous state for every respective edge of the clock signal, like that. Okay. So here these two circuits are the examples for synchronous sequence circuit. Synchronous sequence circuit, because all the flip-flop outputs will respond in synchronous with respect to your action clock signal. Whereas here we will use like n flip-flops. If you are using output of one stage, we will give as clock signal for next stage. That particular phenomenon is called ripple phenomena. Accordingly, the other name for this counter is ripple counter, n-bit ripple counter. Okay. And here if you observe with the help of ring counter or Johnson counter, whatever the states you are getting, those are not following your regular binary pattern. Okay. So these are non-binary counters, whereas with the help of T flip-flops, whatever the counter you are getting, you will get binary up counter or down counter based on the requirement. So that means here you are getting all the 2 power n states. All the 2 power n states you are getting. So because of this, the mod value is mod 2 power n counter. Mod 2 power n counter. So here number of unused states are 0 because all the states we are able to get. Okay, right. So this n-bit ripple counter is an example for asynchronous counter. Is an example for asynchronous counter. Yeah, sure, Hemant. So with this we have completed the fifth chapter. So up to here, whatever we have discussed, it is very important for all the 4 branches, whether you are from EC, Electrical, IN and CS. Okay, first 5 chapters are very, very important for all the 4 branches. Now, let us discuss regarding 6th chapter. 6th chapter is data converters. So here if you observe, we are having 2 types of data. One is analog, another one is digital. So we can convert analog into digital, and similarly we can convert digital into analog based on the requirement. So accordingly you are having 2 types of converters. One is digital to analog converter in short, and another one is analog to digital converter. Analog to digital converter. Yes, very good. Right. So here for this particular circuit, you are having the input digital form and you are getting the output as analog form. Okay. So regarding DAC, we are having 2 types of DAC. One is binary weighted resistor type. Binary weighted resistor type DAC. Binary weighted resistor type DAC. And the other one is R2R ladder type DAC. R2R ladder type DAC. See here, when you are using binary weighted resistor, that means you are using, suppose if you are having n bits, so accordingly you will be having n resistors, okay, but each resistor value will be in the positional weights, in powers of 2 you will get, right? Whereas here, whatever the number of bits, okay, accordingly you will use only 2 types of resistors, but based on the requirement you will use a section R to R. Suppose if R is 1 kilo ohm, 2R will be 2 kilo ohm, like that, right? So when compared to this one will be better, because when you are going for higher order number of bits, right? So to design practically the resistor values accurately or precisely, there may be problem with the help of binary weighted resistor. So that's why we will use R to R ladder type DAC. See, regarding binary weighted resistor type DAC, see in general, if you are having, suppose 4 bits are there, okay, this is the binary number, so you will place the position weights like this: 2 power 0, 2 power 1, 2 square, 2 cube, right? So with respect to position weights, this is the LSB, and this is the MSB in general, okay. But now in the circuit regarding binary weighted resistor type DAC, right, in the circuit, this particular positional weight we will give for opposite resistor. That means this positional weight we will give for MSB. Okay, in this way you can easily remember. 2 power 0 into R is nothing but R. Similarly, this particular positional weight we will give for LSB. So that means LSB resistor value is nothing but 2 power 3 into R. For generalized case, if you are having n bits, here positional weight is 2 power n minus 1, right? So that particular weight into R, that particular resistor value is nothing but resistor value correspond to LSB. Okay, in this way, whenever you are getting the questions regarding binary weighted resistor, so they will give one resistor value, they will ask other resistor value. Okay, so you no need to by heart any formula. So you are very much familiar regarding unsigned case. So just place the position weights here, and you are very much familiar which one is LSB, which one is MSB. So exactly opposite regarding resistors you have to consider. Okay, regarding resistor, the corresponding weights. Okay, right. So whether it is binary weighted or R2R ladder DAC, input is digital, output you are getting analog. So in order to find the output voltage, analog output voltage is nothing but decimal equivalent of digital input or binary input, both are same. Decimal equivalent of digital input or binary input into resolution. I hope all of you know, whenever you are having binary input, how to find the corresponding decimal equivalent. Now regarding resolution, how to calculate? See, you are having formula, by using that formula you can calculate. Okay, I will give 2 approaches regarding resolution. Resolution is nothing but V full scale divided by 2 power n. See, if you are using n bits, with the help of n bits you will be having 2 power n levels, and whenever you are having the meter reading, the full scale reading or reference voltage or maximum voltage, all are same. Okay, so you can consider that value, divide with 2 power n, from there you will get resolution. Or in other words, you might have studied in your analog subject or measurement subject, you might have studied regarding resolution, right? Whenever you are having any ammeter or voltmeter, if you want to observe the minimum change at the output, what minimum change you can make at the input. That is nothing but resolution. Even you might have studied regarding resolution in your analog circuit subject also in the op-amp, right? So now if you want to observe the minimum change at the output, what minimum change we can make at the input? Say for example, I am considering 4 bits. Okay, so initially you consider all the bits are zeros. Obviously you will get output as 0 volt. Output as 0 volt. Now what minimum change you can make at the input? You can make only LSB as 1 and remaining all the bits are zeros. What will be the number of bits? Okay, then you will get the corresponding voltage as, suppose here in this case I have considered 4 bits. So VR by 2, VR by 2 square, VR by 2 power 3, like that. Okay, so for generalized case, so here it is 4. So 2 power 4 you will get. Okay, VR by 2 power 4. Or for generalized case, if you want, you can consider VR by 2 power n, like that. Okay, all are same. All are same. So that means whenever you are having the digital input, the moment if you are keeping LSB is 1, the moment if you are keeping LSB as 1 and remaining all the input bits are zeros, that time whatever the output voltage you are getting, that is nothing but resolution. That is nothing but resolution. Yeah, thank you, Bhavana. Yes, very good. Okay, so in this way you can calculate regarding output voltage and you can calculate the resolution. Okay, so whether it is R2R ladder or binary weighted resistor, the final values are same. Okay, by using these formulas you will get the same values. Okay, regarding operation wise it may differ. Next one is regarding ADC. Regarding ADC we are having, first one is counter type ADC. Counter type ADC, and next one is successive approximation type ADC. Successive approximation type ADC, and next one is flash type ADC. So in the counter type ADC, the maximum conversion time we require is 2 power n minus 1 times t clock. Okay, whereas successive approximation type ADC, the maximum conversion time is n times t clock. Whereas here in the flash type ADC, the moment if you are given the input, you will get the output. Okay, in no time you are getting the output. That's why it is the fastest ADC. Among all the ADCs, this is the fastest. But in this particular ADC, we will, if you are using n-bit flash type ADC, we require 2 power n minus 1 comparators. 2 power n minus 1 comparators we require. Okay, among all the ADCs, this one is the fastest. And here regarding these ADCs, you will get the questions based on maximum conversion time or here regarding comparators number. Okay, so you will get the theory simple questions based on these formulas regarding ADC and DSC. Okay. So with this we have completed regarding electrical branch. Okay, so for electrical branch the syllabus is up to data converters. Now the last chapter, that is CMOS logic family. CMOS logic family. So here you are having CMOS. C stands for complementary, and you are having MOS transistors, right? Complementary MOS. So here we are using two types of transistors. One is NMOS and another one is PMOS. Suppose if NMOS transistor is on, the corresponding PMOS transistor will be off. Or if the NMOS is off, the corresponding PMOS will be on, like that. So when this is on, this will be off, or when this is off, this will be on, right? Yes. Yes, very good, Mayank. Okay, so since these two functionality are opposite or complement to each other, so accordingly the name complementary MOS is there. Say for example, whenever you're having, previously we have discussed regarding logic gates, right? All those logic gates you can implement with the help of the CMOS logic. With the help of the CMOS logic you can implement. Now, whatever the number of NMOS transistors you are using, the same number of PMOS transistors we will use. Okay, say for example 5 NMOS if you are using, 5 PMOS will be there. Together you are having 10 transistors. But during the entire operation, out of 10 transistors, only 5 transistors will be on. The other 5 transistors will be off based on the respective input combination you are giving. That means you are saving the power dissipation or the amount of power consumption required for operating that particular circuit. That means the moment if you are able to reduce the power required, that means indirectly you are increasing the battery lifetime. So that means the main advantage why we are going for CMOS logic, that is the low power dissipation. This is the why we are going for CMOS logic. This is the main reason, low power dissipation. Low power dissipation. Okay, so in general in the CMOS logic, see, you will be having VDD, this is supply 5 volt, and here output line will be there, and here ground line will be there. Okay, so between VDD and output we will keep PMOS logic, that means PMOS transistors we will keep, and between output and ground we will keep NMOS transistors. Okay, suppose if you are connecting NMOS transistors, suppose if you are connecting in series, okay, then the corresponding PMOS we will connect in parallel. Similarly, if you are connecting NMOS in parallel, the corresponding PMOS we will connect in series, like that, vice versa. Vice versa. Okay, right. So now let us see the regarding minimum number of NMOS PMOS transistor pairs required. Minimum number of NMOS PMOS transistor pairs required. Transistor pairs required. So here I am considering the logic gate. So for easy understanding, let us start with NOT gate. So NOT gate output is what? Y equal to A bar. Y equal to A bar. So here you are getting by default, see, here by default output you will get in the complement version, because the moment if NMOS is on, okay, then output will connect to ground. Output will connect to ground. So that means if you are giving, in order to make NMOS on, you have to give high voltage, but that time you are getting output as low. So that means complement, right? So that's why by default in the CMOS logic you will get complement version. Now under the complement you are having only one variable. So that means we require one NMOS and one PMOS. Okay, together we are calling it as transistor pair, right? So whatever the NMOS required, the same number for PMOS, together it is the pair, that's all. Okay, so one NMOS PMOS transistor pair we require. Next one is, let us consider NAND gate. NAND gate. So for NAND gate, Y is AB bar. Y is AB bar. Now just observe same logic. See, you are getting complement version. Now under the complement you are having two variables. That means we require two NMOS, right? Two NMOS we require. Similarly, we require two PMOS. But here you are having logic line. That means NMOS transistors we can connect in series. The corresponding PMOS in parallel, like that. Okay. Next one is NOR gate. NOR gate. So here Y equal to A plus B whole bar. A plus B whole bar. Here by default you are getting complement. Under the complement you are having two variables. So that means you require two NMOS. Since it is a plus symbol, logical OR, we will connect NMOS in parallel, the corresponding PMOS in series. Okay, so pairwise 2. Next, we'll consider AND gate. AND gate. So AND gate, Y equal to AB. AB. But by default, when you are using CMOS, you will get complement version. So first we will get complement. After that, I will apply once again complement. So for implementing AB bar, we require 2, and then for inverter we require 1. So 1 plus 2 is 3. 1 plus 2 is 3. Right. Similarly for OR gate, all of you please respond how many we require. For OR gate, how many we require? How many we require? Same logic. Just apply 2 times complement. A plus B whole bar, just now we got, that is 2. And for inverter, we require 1. So 2 plus 1, once again 3. 3. Right. Similarly, if you consider XOR gate. Similarly, XOR gate, that is A XOR B. See, here you are having A XOR B, but what I have told, by default in CMOS logic, you will get complement version. So that means this one you can write as complement of XNOR. Complement of XNOR. So here you are having A bar, B bar plus AB. And you are having overall complement. See, here you are having AB, that means you require 2 NMOS transistors. same number for PMOS, right? Similarly, here for A bar you require 1, similarly for B bar you require 1. After that, here you're having A bar is like x1, B bar is like x2. So x1, x2 you require 2. So that means 1 plus 1, 2, 2 plus 2 is 4. And here we require 2. So that means we require 6 NMOS PMOS transistor pairs. Now you can apply the same logic for XNOR gate. This is a lost logic gate. A XNOR B. This one you can write as complement of XOR. Complement of XOR. Here A XOR B you can write as A bar B plus A into B bar, and you are having external complement. Now here you are having for B bar you require 1. B bar you require 1. After that, since you are having 2 variables, you require 2. Similarly here for A bar you require 1. Since you have 2 variables, you require 2. So here 3, here 3. Together once again you require 6 NMOS PMOS transistor pairs. So regarding CMOS logic, you will get either the minimum number of NMOS PMOS transistor pairs required, or they will give some circuit diagram. They will ask the output. Okay. So in this way you can answer any question. Okay. Right. Very good, Mayank. So in this particular session, we have discussed for all the chapters, for all the 4 branches regarding digital circuit subject. So we started with the number systems and codes, then we have discussed Boolean algebra and K-maps, then logic gates, combination circuits, sequence circuits, data converters, and CMOS logic family. I hope all of you got the quick revision, okay, in this entire session regarding overall subject, digital circuit subject. I hope all of you got the confidence regarding this subject. So all of you kindly share your experience about this particular session. I hope all of you got the confidence, and I hope all of you got lot of interesting points and important points, formulas, everything regarding this particular subject. Yeah, thanks a lot for all of you for attending this live session. So tomorrow we are having the live session regarding measurement subject, so which is common for electrical and instrumentation. So Nikhil sir will take that session. So those who are from electrical branch and instrumentation branch, tomorrow electrical machines quick revision session is there. So those who are from electrical and instrumentation students can attend that live session. Yeah, regarding Mealy and Morey, those are state diagrams. Generally they will ask the sequence detector. Those are the simple questions. Just by observing the state diagram, you can observe which sequence of bits it is detecting. State machine is nothing but simply it is just pictorial representation or diagrammatic representation of the sequence circuit. That's all. Yeah. Yes, Mayank, definitely. I will come regarding quick revision session of communication subject on 28th. On 28th January. Next week I will meet. So those who are from EC and instrumentation, we are having one more session regarding communication system subject. So that session will be on 28th next week. Yeah. So definitely in that subject also, from first chapter onwards, for each and every chapter I will discuss for each chapter all the important points and the formulas which are important with respect to subject and exam point of view. Okay, right. Yeah, thanks a lot for attending this live session. So for the time being, I'm stopping here. We'll meet you all in the next session. Okay, thank you everyone.